Okay, I think we are ready to start. So, good morning, everybody. For those who are attending online from other countries, welcome from Turkey. Today, we are here for a training school on NIR spectroscopy. But before starting our lectures, I would like to shortly talk about our project of which this training school is being organized. So SuChAQuality, sugar and chocolate authenticity and quality, is a Marie Curie RISE project, and RISE means research and staff exchange. And this project is a Marie Curie project covered under Horizon 2020, and we currently have 11 partners from different countries, including industrial partners as well. So Metu, Kayseri Sugar Company, Drukan Confectionery, Tören Chocolate, University of Warmia Mazuri in Olsztyn in Poland, Resonance System in Germany, which is an NMR instrument producing company, Nottingham Trent University from UK, SG Isotech from Serbia, University of Concepcion from Chile, and we have NUST, National University of Science and Technology, Islamabad from Pakistan, and Stellenbosch University from South Africa are our partners. And under RISE project, we are performing exchange, which is called in RISE terminology, secondments between partners to transfer knowledge. But while we are doing this, we are also trying to do as much as dissemination activity as we can. And our goal in the project is to utilize different analytical techniques to develop quality control methods for confectionery and sugar industry. And under this main objective, we have NMR, NIR, stable isotope, XRD techniques as the main techniques to be utilized for confectionery and sugar industry. Now I will show a very short video about our project. Okay, so this was about what generally our project is about. We are in the social media and trying to post all our dissemination activities to our Instagram and LinkedIn and also Twitter accounts. We also have our webpage, SuChAQuality.com. And this is our work package. So we have NMR, FFC NMR, mobile magnetic resonance hardware development, use of NIR and IRMS on sugar and confectionery products, data analysis as our main work packages. And this training school, which is going to be held by our South African and Chilean university partners, is being performed under the scope of work package 5, which the goal is use of NIR on sugar and confectionery products for method development or validation. And as you will see in the lecture, we will try to give you a basic understanding of near-infrared spectroscopy. Now I will leave the floor to Professor Marena Manley from Stellenbosch University, as she will be holding all the lectures in the morning session. Floor is yours, Professor Marena.
Günaydın, and thank you, Hocam. Thank you, Meche. Thank you for the introduction. Yes, I must say I've been in Chile now. Oh, no, I'm not in Chile. In Turkey for the last 3 months, and it's really been a privilege to be in the laboratory of Dr. Ostop, to be in the Ostop lab, and it was really exciting. While I was here, they moved into brand new laboratories. So it's really been a privilege to be here and just be in such a vibrant research environment where there's students in laboratories all day. Sometimes it seems like all night as well. So there's just been so much activity, and it was really great to be part of this experience. So this is my last week in Turkey, and a privilege to be able to present this course. So thank you very much, Ejit, for the introduction and the opportunity to do this, and also the opportunity to be in Turkey for such a long time and had such amazing experience and meet so many amazing people. I can see we are quite a number of people, but I thought maybe, oh goodness, this is quite a lot. I don't know how long this will take us. I thought if as many as possible can maybe just switch on their cameras so we can at least have Zikru can get a picture of everybody attending. We'll just swap to both slides, both pages. And maybe if a few of you, I know some Typhoon, Ege, Osan, Zikru, Esra, Furkan, they're just sitting around the corner from me, but I know there's a number in Chile, and I believe it's still really early in Chile. And I've seen one from South Africa. So maybe if a few of you wouldn't mind just to introduce yourself and just briefly tell us where you're from. Do you have any experience in NIR? So who shall we start? Shall I just point a few names? Vladimir.
I think that's a good idea. Yeah. One thing in between. Yes. We will be recording the training so we will be posting it later to our webpage. If you have any objections on this, we just would appreciate if you let us know in advance. If it is okay, then we consider that it is safe to record. So the lectures will be available afterwards in our webpage. Okay? Yeah. Okay, now.
Okay, so I'll just use 5 minutes or so just to get an idea of who's our audience. So let's start with Vladimir. I hope you don't mind me just picking names. If you don't want to speak, just tell me. Vladimir?
Yes, we don't have on mine. Hello, as Marena said, I'm Vladimir Kitanovsky. I'm coming from North Macedonia. I work as a university professor at the University Mother Teresa in Skopje, which is a public body. I am at the Faculty of Technological Sciences. I am working especially in the field of food technology in that study program. So the experience with NIR, I've got experience as a member in the Sensor Field Cost Action. That's where I got the information about this today, the training session with NIR. I was awarded with one grant for short-term scientific mission that I realized in Católica University in Porto under the lead of Professor Antonio Ferreira. And at the end of the short-term scientific mission, there were one international workshop where I met all known names that are working many years ago in this kind of field. So that was like a beginning, and on my luck, not so far ago, we equipped our laboratory with TIR, NIR, and everything. So now I can work at the laboratory in Skopje, and that's why I want to expand my skills and expertise to this topic. Thanks to all, and thanks to this beautiful opportunity to work and to hear and to see everything from experts like you.
Thank you, Vladimir. And Hilmi, I see Hilmi is also awake. What time is it in Chile, Hilmi?
Hello, Professor. It's 2 a.m. now.
Okay, so thank you from Chile getting up this early. And then maybe I see there's one person from South Africa. Naomi, maybe you can just mention briefly, just introduce yourself briefly.
So you want me to introduce myself?
Yeah, no, you can introduce yourself. Yes, please, Hilmi, and then I go to Naomi. Yes.
Oh, okay. I'm a graduate student in Middle East Technical University. I'm also one of the ESRs in SuChAQuality project. So I'm working on hyperspectral imaging, chemometrics, and also NIR. We are trying to differentiate between sugar beets and sugar cane, most likely, and decide the sugar amount just by looking at sugar beets. So for now, I'm in Chile also. 3 days ago, I was in here, and I will work on chemometrics in here. So I think briefly, that's all.
Okay, and Naomi, are you there? I've lost Naomi now. I can't see Naomi. I see Job and Francis.
Can you see me now, Prof?
Yes, yes.
Okay. Good morning, I'm Naomi Douglas. I'm currently a fourth-year student from Stellenbosch University, and I'm planning to do my master's under Prof Manley next year, also with NIR and chocolate quality.
Okay, thank you, Naomi. Okay, and I've asked Job and Francis. Oh, I think you muted, Jobin. Just check that you're not muted.
We can't hear you.
No, we can't hear you, Jobin. Maybe while he's sorting out his sound, anybody else? Oh, okay, he's typing. Who else shall we ask? Mario. Mario, can you hear us?
Yes.
Okay.
I don't have my camera.
That's okay.
Well, my name is Mario. I'm from Chile. I am a PhD student. No, I have the degree now. Sorry. And I worked a few months ago to Turkey when I learned a lot about a lot of things. My main field is chemometrics, and also I work with hyperspectral imaging. That's all. Thank you very much for the presentation that we will see.
Okay, thank you all. I think during the course of the 2 days, I will sort of get more people to introduce yourself, or if any of you have questions, then before you ask your question, please just feel free to introduce yourself. Thank you, Jobin says he's from NTNU and he's also started working with hyperspectral imaging. And I can see already there are people with experience and quite a lot of experience in NR spectroscopy, but I know there's also some with no experience. So for those who do have experience, I really want to invite you as I present, and you want to add something, or you can maybe explain something in a different way to make sure everybody understands it. I will really appreciate it. And also as I present, please feel free to just interrupt me at any time during the presentation. I've been teaching for 25 years, so I'll be okay to be interrupted at any time. I think, yeah, that's just for the introduction. So let's get started. Let me just share my screen. Okay, So I just want to move this a little bit out of the way. Okay, so everybody can see my screen. Majid, if somebody can just indicate, I'm sure that's okay.
Yes.
Yes. Alif is sitting behind me, so she can also keep me updated. Okay, so as you've seen in the training advertisement, we've split up the training in 9 separate modules. Some of the modules will be taught by me. I will cover really, as I've indicated on this slide, the practical implementation of the use of near-infrared spectroscopy. And so I will not in detail cover the physics and the optics of the instrumentation. I will also not cover information such as the Beer-Lambert law and why that relationship, which states that there's a linear relationship between the concentration and the absorbance of a liquid or solution. That means that if you can determine the absorbance, you can calculate the concentration. Because NIRS measures mostly in reflectance, the Beer-Lambert law does not really apply. Also, the Beer-Lambert law has limitations when it comes to applying it to scattering materials. So I'm not going to go into the detail of that. If any of you really want to learn more about the physics, the optics, the actual how the instrumentation as such work, then you'll have to let me know and we can organize an additional session for that. So I will cover the practical implementation. I will start with the introduction today. And then I will look at some terms that one uses to evaluate your calibrations once you've developed the calibration. And I thought to do just a basic introduction to chemometrics. That's almost how, I'm not a chemometrician, so this is almost how I, as a non-chemometrician, see chemometrics or experience chemometrics or use chemometrics. So Professor Rosario will do it in much more detail. So I hope that this might help those who've never worked with chemometrics to understand what she would be doing in much more detail. So I will do the basics. So if you want to know more about the intricacies of the topics that I will cover today, then you have to ask Professor Rosario this afternoon. And then just as an introduction to myself, I'm from Stellenbosch. And if you can see here on the left-hand corner of the slide, you can see Cape Town, the right furthest near Cape Point. Stellenbosch is about 60 kilometers from Cape Town. And as I've shown on the slide to the left, Stellenbosch is situated amongst many, many vineyards. There's just around Stellenbosch, there's 100+ vineyards, and not just produce, they produce amazing wines. Most of them also have really excellent restaurants. And Stellenbosch itself, the university produces its own wine. This is the Bottled D line as one of the university's wines. And Stellenbosch is really well known for its Cape Dutch buildings. It really has beautiful Cape Dutch architecture, and you will experience when you visit Stellenbosch that it is really white. All the buildings are white. So this is just a little bit about Stellenbosch. And I'm at Stellenbosch University. I'm from the Department of Food Science. The university itself celebrated its centenary 4 years ago. So we've just been 100 years old. And to the left was our old branding. We just changed our branding to the one in the middle. You'll see the oak leaf to the left and also the oak leaves in the picture to the left. Stellenbosch is also known for all the oak trees that grows all over the town. Okay, so Stellenbosch University with its new branding, and our department this year is 70 years old. So this is exactly 300 years after Jan van Riebeeck arrived in Cape Town with these 3 small ships. And that event really had a significant impact on our country, and which led eventually to the form or the start of the Republic of South Africa. Okay, so this, I just want to mention, so this module, I will really cover introduction, a little bit of history, and I'm presenting this in association with Dr. Phil Williams. And you will see a bit later, I will explain a bit more where he fits into the picture of NIR spectroscopy. And I had the privilege to work with Phil for a number of years. I visited his lab in Winnipeg when I was a PhD student. And a couple of years ago, I realized that Phil used to present training courses at a number of conferences. And he had this PDF document. So when he presented training, he would just hand out this document to some students. And I realized that there are such a lot of amazing information and useful information in that document. And I managed to get funding from our university, and I assisted Phil to publish his training material in the form of a book. And what's really valuable about this book is that it contains Phil's experience, which he gained over 40, 50 years. So there's really many, many years of experience included in this book. And so the training I'll be presenting is also based on this book. The book is available as a hard copy at Amazon.com. I've provided the links below. And also, so Amazon provides it as a hard copy. And from African Sun Media, the book is available as a PDF. So based on what I'm presenting, there will be a lot more detail included in the book. The cost at Amazon is about, in Turkish lira, about 450. The African Sun Media PDF book is about just over 300 Turkish lira. So I'm not sure now how much it is in euros or dollars. So in South African rand will be similar, about 300 rand, about 450. So this is really quite useful. But I still have some copies in my office. So anybody who's coming to visit me are welcome to get a copy from me. Okay, so I just wanted to introduce Phil. He's currently 89 years old. I still speak with him regularly. I must admit, I tried to make contact with him this week. I haven't had any response from him yet, but I hope to hear from him while we're still doing the course. Okay, so that's Phil, and he really did some amazing work, as you will shortly see. Okay, so okay, I think I've skipped a slide. Why is my slides not moving? I've got pictures in my way. Sorry, my slides are not moving. Okay, there we go. Okay, so why do we need NIR technology? Why do we need to know about it? Why do we need to learn about it? One of the amazing things of NIR technology is it really provides you the ability to test samples that you would practically not being able to test without NIR technology, purely because analytical techniques use a lot of chemicals. It's really time consuming. And if you can calibrate an NIR instrument, it really gives you the opportunity to analyze those samples, to analyze many more of those samples, and to do it in a really rapid way. And to the left of the slide, you can see a typical laboratory instrument. And with this instrument, you can really see. I just have to ask Alif somewhere, where can I move my piece so that's not in my way? Oh, there it is. That's better. Sorry. I had all the images, the pictures in my way, and I couldn't see my slides. Okay, to the right, you can see a typical laboratory instrument. That's a Bruker MPA. And with this instrument, you can do whole grain samples. You can do liquid samples in an auto-sampler. It has fiber optics, where you can just scan a sample in a container. So it really provides you with a huge range of opportunities to do a different types of scans. And at the bottom, we have a handheld instrument, which we can get nowadays, where you can really go anywhere and analyze some samples. Okay, so apart from the fact that with NIR, it really allows you to do analysis in an economical way that you might not have been able to do in the past in the same way. With NIR, once it's calibrated, you can really, with one analysis, test a number of parameters. So if you have You'll see that a lot of my examples will be on cereals because that's the field that I've worked in mostly. So if you can analyze damaged starch, protein, moisture, gluten content, if you have those 4 parameters calibrated for, with a single scan, you can predict all 4 parameters. So it really provides you that benefit as well. In a factory, it really enables you to monitor processes from your ingredient right through to the final product. You can screen and analyze thousands of samples in a few days. It's not the most exciting thing maybe to do, but if you just stick to it, you really can analyze thousands of samples. NIR is a secondary method, so maybe I should mention that already now. So that's not an instrument that you can just buy and immediately measure something. So it needs a calibration. So it needs to be calibrated against something. So therefore, you need a reference method, and it's really important to know the accuracy of the reference method so that you can compare the accuracy of your NIR calibration with that. And we've seen that you can develop calibrations where we really get comparable accuracy compared to the reference methods. And then what we often see is that the reproducibility of the NIR is often better than the reference method because of the complexity often of the reference methods. It's difficult to get a good reproducibility, but with NIR you can really, might not necessarily be at the same accuracy, but at least it will be reproducible. So something that we nowadays see with NIR instrumentation is when I started with NIR, you buy an instrument and then as it sits there, you couldn't really do anything with it unless you've calibrated it. So we used instruments to develop calibrations. Nowadays, instruments are provided by companies and they arrive already factory calibrated. So especially in cereal science, over many years of cereals being analyzed, there are huge databases. So for example, this Pertin instrument to the left, it's also actually a portable instrument. You can buy this instrument. It already would have calibrations for, say, wheat, protein, moisture, starch damage, gluten content, and you can just measure it straight away. Similarly to the little SIO at the bottom, a small handheld instrument or miniature instrument, you can scan a sample, and what they do is they have calibrations in the cloud. So you scan your sample, it works via your cell phone. The spectra is taken, it's sent to the cloud, it's fit with the calibration, and you get your result back. So this are ways how NIR instruments work at the moment. So the question now immediately comes, do we really need to know how to develop our own calibrations? Do we really need to know that much about NIR instruments if the trend is to use instruments with already calibrated or arrive with factory calibrations? But let's see, do we still need to do more? So as I said, for wheat samples, there are huge databases. So there are calibrations available to make life a lot easier. But often, and I've seen also working here now at METU, there are cases where people really want to develop classical calibrations. And that means it's something unique which hasn't been done in the past. So in that case, you really need to do your own calibration. And that would be small sample sets, maybe ideally 100, sometimes up to 500. The large data, the wheat science databases often go up to 30, 40,000 samples. So it's really huge databases. But with 100, maybe up to 500, you can really do good calibrations. However, once you have these factory calibrations, they still need to be monitored and maintained. So you need to check on a regular basis that calibration is still accurate for the type of samples that you analyze at the time. So we still need to know how to develop calibrations, and even more importantly, we need to know how to test calibrations. We also, you would like to improve your operation, and you want to make more money using NIRs. So we really need to test NIRS and make sure, or we need to test our calibrations and our systems that we have, and to improve it as best as we can. And then what we can, well, what we obviously, we sit the whole time and think, what can we do with NIRS that can make our life easier that we could not have done before? Yeah, so if you have, okay, so some of this application I'm showing now is if you should have a calibration or instrument in the factory. So we need to verify that the calibrations that we purchase is still valid for the commodity that you purchase it for. Often you would have a calibration, but your samples might come that you're going to test in future, might come from different seasons, different growing locations. It could be different cultivars. In industry, it could be that you've changed some of your raw materials. If that is the case, then we need to update our calibrations. And we need to know how to do that. As I said, there might be specific needs. Suddenly there's just completely different applications that we would like to test. And what is important is that to run an NR operation, to use an NR instrument in your factory or in your research group, it's more than just operating the instrument. So you really need to know the entire process of having an instrument and using it effectively. Troubleshooting, you need to do troubleshooting. So to do that, you really need to check the diagnostics of your instrument regularly. You need to know how to interpret diagnostics. You would have check samples to make sure that your calibrations are always performing the way it should do. And to do this, we would do what we refer to as calibration model development. So if we look at the life cycle management of NR spectroscopy, so the process that you would go through, so if we want to develop a new calibration, first would be data collection or sample collection. And for that specific sample, if you want to do a quantitative calibration, you would need a reference method. You need to select calibration validation sets. And there's also important aspects that needs to be kept in mind when you select those sets. You have to select your samples. One way, I might just mention it now before I forget, when you collect your data, so say you've got 500 samples, and we know the cost of reference methods. If you have to do HPLC to determine those samples, the reference method or the reference result, it will be quite costly. So what you could do is first look at your spectral data. You could do a principal component analysis. You can see how do your data compare and fit with one another, and you can select a sample, a smaller sample set that's still representative of the entire sample set, and then start with that smaller sample set, get the reference methods done, and start with the calibration, doing it that way. So that will, at least in the beginning, save you some money. So first, the selection of the sample. And I'll get back to that as well. Selection of samples is really important. How do you select your samples? Sampling for reference method as well as for NIR is really important. And it can introduce huge errors if that's not done properly. So once you've got your data, you need to calibrate, and that would involve pre-treatment of the data. We'll get back to that. I'll get back to most of these in more detail later on. You do your model optimization, assessment of your model, and then we will do a proper validation. Validation could be from a set that you've selected from your initial population, or it can be a completely independent set which you've collected at a later time. So that would be a means of really testing your calibration. And it should be done in such a way to also test the robustness of the calibration. That means that the calibration would not just be effective for a small sample set, but it will really be effective once you use it in a larger sample environment. Okay, then maintenance is important. So you need to check on a regular basis, is your calibration still working appropriately? That you need to check. And this is something you have to remember when you implement NR in your company, for example. you need to make sure you budget for this. So you have to budget for model maintenance. So you will check the model on a regular basis and using a model maintenance roadmap. I'll show you that in a minute. And that might determine whether you need to recalibrate, whether you can just adjust the calibration, or whether you can just maybe do some slope bias adjustments. And if necessary, you will do a recalibration by looking at the scope of your calibration. Do you now have a wider range of samples that needs to be included? And again, instrument performance verification needs to be done all the time. And once if you have to redevelop, you might add some data and you just continue with this continuous circle. And I'm just going to show this briefly. This is the NIR roadmap, maintenance roadmap. So you could, where do we start? I'm not going to go through this entire process in detail, but you really need to set up a roadmap such as this for yourself if you want to check whether your NIR system is still working properly. So you will develop your calibrations, you will develop your maintenance plan. So you put your model or your instrument online, say it's an online facility, we want to measure protein in wheat. And then you check the performance by, in this case, maybe you'll do some measurements and you test a few samples with the reference method. If everything seems okay, then it's fine. You can just use your calibration. The problem comes when you test one day and it's not in order. Now you have to figure out what could be the problem. Is the sample you added out of range from your calibration? So does it not fit your calibration set? Did the relationship change? Did the instrument change? Did the sample change? Is there something else that's currently interfering? And this way you will just have to follow this. So if the samples was out of range, you suddenly get new samples that does not fit within the range of your calibration. So say I've got a calibration working between 12 and 16% protein. Now suddenly I'm getting samples 9% protein, 18% protein. They're not going to predict accurately. So now you have to get more of that range of the sample, add it to the initial samples, calibrate a new model, or in other case, if there was a smaller interference, you just saw a bias, then maybe you can just correct for the bias. So suddenly you notice all your samples measure 2% lower. Then it's acceptable to just make that bias change so that it will fit your calibration again. So it's important when you use NIR spectroscopy in industry that you really have such a maintenance roadmap to follow. If something goes wrong, that you need to know which road to follow. Okay, so what do we need to know? Maybe at this point, where's Typhoon? Before I start, Typhoon, I spoke to Typhoon. I spoke to Typhoon. Can you switch your camera on, Typhoon? I spoke to Typhoon recently, and he started not that long ago with NIR spectroscopy. And all he said to me was, everything he tried to do was difficult. Everything was difficult. So, Typhoon, maybe you could just elaborate how you experienced starting with NIR.
Yes, I can. So I've started to work with NIR from scratch like 6 months ago. And up to now, I am trying to improve on NIR and gain some basic knowledge about it. So currently I am doing a study about ascorbic acid content. I mean, analyzing it through the NIR. And so I have been struggling, and because of that, I have talked with Professor Marena, and said it was a difficult process working with it. So I have struggled with, especially for sample preparation and doing the calibration model, because it includes chemometrics, and it's a whole new area for me, all those terms and pre-treatments and other things. So it's a hard journey for me.
Thank you, Typhoon. And Typhoon also said to me, when he started with his work, he started reading papers. And then when you start reading NR papers, and this is the one thing you see, which you will see today, is this is, for example, those of you who are familiar with cereals. If you want to analyze a wheat sample, you have to run about 10 tests to say what is the quality of that sample. And when you do NR calibrations, you have to interpret about 10 different terms to be able to say, okay, my calibration is okay or not. And Typhoon was saying he started reading these papers, and there were just so many terms that everybody used to explain the quality or the accuracy of the calibration. So that was quite tricky, and then to find out exactly what all those terms mean. So I hope by the end of this course, also with the help of Professor Rosario, all of those will be a lot easier. So thank you, Typhoon. So just then quickly, what do we need to know? What is important to know when you want to run NR operation? The first thing you have to look is the most suitable instrument. When I started, it was reasonably easy because there were 3 instruments. So you can say, if you want to do food, this is the best one. If you want to do feed, this is the best one. One other application, this will work well, or pharmaceuticals. So there really were such limited instruments, but nowadays there are a huge range of instruments. So you really have to do some homework to check which instrument will be most suitable for your commodity, for what you want to measure. You have to make sure how to run an instrument efficiently. You have to make sure you maintain your instrument. Then you have to, once you have, even before calibration, you just have to monitor the performance of your instrument. So all of these instruments can run their own diagnostics. You have to run those diagnostics regularly to make sure that your instrument perform well, and you have to be able to interpret those diagnostics of the instrument. If your analytical performance is not performing well, you have to learn how to recognize when that starts happening, how to calibrate, and this is now where the chemometrics comes in, and Typhoon can maybe explain later as well, is some of the instruments with dedicated software, they have like a wizard. So for those who's not as familiar exactly how to go about the first steps, so you can just ask the software, say, I want to calibrate, I have a ascorbic acid solution, so I want to calibrate ascorbic acid, then I just ask the software, run the wizard, test as many pre-processings as possible, test as many things as possible, and give me all the results. And I can pick more or less, this would be the best pre-processing. So that's a way of learning. By running the wizard, you can really get an idea for your sample what type of pre-processing would work. So how to calibrate the instrument, you can do it, if you're really experienced, you go maybe to MATLAB and you can decide how to go about it. But if you're not as experienced yet, the software that comes with the instrument is really as such to help you to go through this learning process. Okay, then you have to evaluate how to evaluate the calibration, and that's where you need to know all these different terms. Okay, you have to understand the basic of the statistics, you have to try and get the best from your software. Sometimes you need to extend the scope of your instrument, and as I said earlier, improvement and maintenance of your calibration. Is there more? Sorry, how to improve and then maintain your calibration. So NIR spectroscopy is really this is in my way again. It's really a joint effort between spectroscopy and statistics for chemists, or chemometrics as it has been referred to since the early 1970s. It's a term that was started being used by Svante Vogt. So chemometrics specifically referring to statistics for chemists. Nowadays, I see that people tend to use the term multivariate data analysis more often. And then obviously, as you might have seen, people now doing machine learning and all other algorithms trying to include to use that as well. So again, for NR instrument to work effectively, it must be calibrated. And if you want to do a quantitative calibration, it must be done with well-known and accurate reference methods. And so the calibrations are based on a mathematical correlation between your spectral data and your reference data. And once that's developed, we refer to this mathematical correlation as a model. So the first thing we need to do is, and that is important, we have to know how accurate our reference method is. So I will spend more time on the reference methods tomorrow because I want to do a bit more on chemometrics today. So it is important that the first thing you do, you have to know how accurate your reference method is, because that accuracy will affect the accuracy of your calibration. So with chemometrics, you learn how to do this mathematical correlation between your spectral and your reference data to develop an equation, which we refer to typically as calibration models or prediction models or validation models. The one thing one always needs to have to take in mind is the cost of an instrument. The NR instruments do not come cheap. I remember the last time I checked, they were already over R1 million or 1 million Turkish lira. So, but if you take that in consideration compared to the value of the commodities that you are testing, then it probably just is clear that it's not going to be a waste of money to purchase such an instrument. So if you ask the question, what will the consequence be if you don't test those materials? Then you realize it's definitely worth the while to purchase such an instrument. So although they cost a lot of money for what you're going to use it and the money you're going to save over a period of time, not having to do expensive analytical methods or losing product because you couldn't test it properly, it's just obvious it's not going to be a waste of money. So the main objective of the part that I'll be doing today is to learn how to get the best technical performance from your instrument and how you get the best technical performance from this fascinating technology. Okay, but let's start at the beginning. Let's go back, what is it, a few hundred years. Frederick William Herschel, he was a musician and an astronomer, and he discovered NIR light. And what he did was he was looking at the colors of the rainbow. That's why I call NIR at the end of the rainbow. So he was looking at the spectrum with the different colors and just using the light coming through his window. And he had the thermometer line just beyond the red. And then suddenly he noticed that the thermometer, the temperature on the thermometer increased. So he realized there was something beyond red. So he's acknowledged for discovering NIR technology or IR technology. And NIR technology, as you know, goes from sometimes people say 780, 800 to 2500. Visible goes from 380 to 780 nanometers. And then the mid-infrared region from 2500 upwards. But at the time, NIR technology was not really considered useful. It was easier to understand the analytical methods they used at the time. They used mid-infrared mostly to determine molecular structures, but they just couldn't figure out how to use NIR technology. And they just started to believe that there's really nothing to be gained from NIR technology. And the people thought, and students were taught at the time, that that's not really a useful technology. So nobody was taught anything about NIR technology. And it was about 150 years later that Carl Norris came to the rescue. Carl unfortunately passed away 3 years ago at the age of 89, and he was really still active until that age. So Carl was an engineer. He worked at the USDA, the United States Department of Agriculture, as an engineer. Because he was an engineer, he was never taught spectroscopy. So he didn't know that there was nothing to be gained from spectroscopy. So similar to Herschel, he looked for something where there was supposed to be nothing. But what Carl then realized, and I think that made a huge difference, he realized that there are certain requirements for the NIR region to be useful and applicable, especially for agricultural applications, because that was what he investigated at the time. So we realized that you need a spectrophotometer with low noise, you needed an electronic computer, and you need to use mathematical techniques. He realized that there was a relationship between the absorbances and the concentration of a sample. So having realized these three requirements, spectrophotometer, computer, and the application of mathematical techniques, he developed an NIR instrument. And that development led to the first commercial instrument ever being developed. And this instrument below here is the instrument that Carl actually developed, when is it now, almost 70 years ago. And the instrument still sits at the USDA, it sits there in a small room. So this was the very first research instrument that Carl developed, which led to the New Tech Corporation. And because of this, Carl is really acknowledged, and he has been acknowledged all these years as the father of NIR spectroscopy. Then, more or less at the same time, when Carl was doing this work in the late 1960s, further up north, the Canadian Wheat Board decided to sell their two top grades of Canadian hard red spring wheat at guaranteed protein levels. So if the farmers could provide that wheat at a certain protein level, they will be paid accordingly. And that meant a huge number of protein analysis to be performed. So Phil was appointed at the Canadian Grain Commission as the chemist in charge of protein determination. So you can imagine, those of you who've done Caldol analysis, that's the way it was done at the time. They had a huge Caldol laboratory at the Canadian Grain Commission. You can imagine the amount of sulfur, all the chemicals that's been used, how time consuming it is, and it's thousands of samples coming in from producers. So Phil then tried to find ways of means to doing it better and easier. So he made some modifications to Caldol. It didn't really help. And then in the early 1970s, 1971, Phil heard of what everybody called this miracle instrument from New Tech. And after took some time, but he managed to convince his director to purchase this instrument for him. So Phil bought this New Tech instrument below here, which was probably the first ever instrument that was purchased for industrial use. Then Phil started doing analysis, and Rob Rosenthal from the New Tech company came to Phil and said, okay, I can design an instrument for you that can scan 10 samples in a minute. And Phil then immediately say, no, thank you, because it's not going to work, as nobody will be able to load 10 samples fast enough. And he then suggested if they could turn the instrument upside down, they can develop this tray with the samples. And then he has a tray with 10 samples. And if this can move underneath the instrument, he can scan those 10 samples in a minute. And that's what they did. And that led to the development of the automated digital analyzer. And this was the first NIR instrument to use a digital computer. Okay, and from then on, Phil just continued testing, developing calibrations, measuring more samples. And at the time, one of the only disadvantage here was the sample still had to be built to be analyzed. But he tested for about 4 years, tested, developed calibrations. And then eventually he got a good enough calibration. And then 1st of August, 1975, Phil remember these dates exactly. Without telling anybody, he changed the whole wheat protein segregation operation in Canada from Caldol to NIR spectroscopy. So this was really the first industrial application of NIR spectroscopy. And this has really made a huge difference. Since then, people realized that NIR can be used effectively. It can be used in industry. And from then onwards, one just saw so many people doing research on NIR and develop more instruments and use it more effectively. And similarly, one can do a similar story for chemometrics. I'm not even touching on chemometrics. At the same time, it developed from using multilinear regression to where we are now, where there are a range of sophisticated NIR technology methods that can be used to effectively analyze and calibrate instruments. Then in the 1980s, so this was 1950s and 1980s, the first whole grain analyzer appeared or was designed. And that made a huge difference. Not having to mill the samples just resulted in so much more samples being analyzed in much faster. Okay, and for he's been awarded all over the world for the work he's done. And I visited him in 2018, and he was really dismayed knowing that he's never been acknowledged in Canada for the work that he's done on NIR and for the wheat industry. And it was really great for me to learn that last year he's been awarded by Canada, and his painting is now hanging in the Canadian Agriculture Hall of Fame gallery. So he's been now awarded in his own home country for the work that he's done. Okay, this is just two more instruments. The specific scientific model 635 was the first scanning instrument. Until then, I haven't mentioned it now, those earlier instruments only worked with specific wavelengths. They knew which wavelengths are suitable for analyzing wheat samples, where protein, moisture, starch, something that would indicate particle size. So they knew which wavelengths would be suitable. And the specific scientific model would be the first scanning instrument that scanned the entire wavelength range. And this instrument to the left, I remember Phil once presented a course for me in 27. Yeah, I think it was 27. And at that time, I think it was in Lebanon or somewhere, this instrument has been operating for 40 years. So once you have an NIR instrument and you look after it well, it can really operate for a very long time. Just some more interesting information. Phil and Carl actually, they were doing this work independently, and they actually only met in 1973, and Phil had the opportunity to work with Carl during 1976, 1977. And when I spoke to him the other day, he said that was still the best part of his careers, to be able to work with Carl for that time. They then together wrote the first monograph. The first actual book on NIR spectroscopy was written by Brian Osborne just a year before the monograph, and they then edited this monograph with contributions from different people. It has been a new edition appeared, I think, a couple of years ago. And then I just want to mention the book again, which Phil then published in 2019, which really just shows everything that is done and tested on NIR during his long career. Okay, so since this first use in the cereal industry, NIR spectroscopy has really become the quality control method of choice in many, many industries. And there, as you can see here, there's a huge range of instruments available, and many more applications are now are possible to do because of advancement in instrumentation. Huge difference was made by advancements in computing power, and then also development in multivariate data analysis, different techniques that's been developed that really improve the development of calibrations. So this to the left here, we have a handheld one, and then also what one see is also having instruments online. So if it's positioned online, you can imagine where in the past you had to sort of take a sample, you could only analyze certain batch samples. With having an instrument online, you can really do continuous measurements. Then the need, was quite interesting, the need for portable instruments was there early on, and somehow the instrument companies really struggled to develop a stable portable instrument. But in China, they had problems with counterfeit drugs, and they really, really needed to test it all over the country. And the only way they could think, or was possible at the time, to get a portable instrument was to equip about 400 vehicles with NIR instruments. So they installed these 450 vehicles with Bruker. It was the Matrix F with Bruker instruments, as you can see here. So the cost of this, but that was really the only way to get a portable instrument, and it worked. So at least they could go to a facility, scan the samples just with the push of a button. But since, okay, the next portable instrument that became available was the phaser instrument. Sorry, I'm just going to close this door quickly. Sorry, so the phaser was the frame. It was still bulky, but it worked well. But then since 2013, we've seen the development of miniature instruments, and they are reasonably stable. So the JDSU was the first really stable miniature instrument that became available in 2013. It has since been updated to the Vihavi and replaced by the Vihavi instrument. I will probably, if I remember, mention it again. Vihavi has also a process analytical technology device, which you can actually, if you do blending of a sample, which you can actually install in your blender. And as you're blending your sample, it will make measurements, and to the point where it can see there's no more differences in the spectra, you know you've done appropriate blending. So there are small devices nowadays that can be included in process analytical technology, or where PAT is being done. Then we have the SIO, which is done by an Israeli company, and they claim that maybe this could be used by consumers. You can go and measure the sweetness of your apple or your fruit. The Nir scan, they're trying to develop this for measuring wheat samples in Canada. It is quite tricky. It has quite a small lens, as you can see here. So it probably only covers a kernel at a time. So you need to do a number of measurements to make sure it's done effectively. And we're not really going to cover hyperspectral imaging. One can cover that in a later session if you're interested. But Stellenbosch University, Dr. Paul Williams just purchased the Spectrum IQ. So those of you coming to visit Stellenbosch might have the opportunity to use this Spectrum IQ, which is a portable imaging camera. Okay, so NIR instruments can scan, depending on the instrument, it can scan the entire range from 3 IT visible up to 380, which is visible, up to near infrared. The spectra are typically recorded in apparent reflectance. So what is measured is reflectance, and it's recorded as log 1 over reflectance, or if it's done in transmittance, where the light goes through the sample, it's measured in log 1 over T. We'll see nowadays that the terms, okay, you can use the term optical density, but we see nowadays that people rather use the term absorbance, and one doesn't really see as much log 1 over R or log 1 over T. To me, it's important, I think, that you should not, don't present your results as reflectance. Although reflectance is what is measured, but should convert it to absorbance, because people working with NIR are familiar to see absorbance spectra or log 1 over R spectra. So if you suddenly come with reflectance spectra, it just does not look familiar to people. The other thing is, and I'll mention it now already, is if you use FTIR instruments, you'll see that they often record the wavelengths in wave numbers. So instead of 400 to 2500, you'll have 12,000 to 4,000. And it also turns the spectra the other way around. So then people are really confused. And also, we are used to, 4030 is moisture, 2100 is protein, 9040 is where moisture absorbs. So if you know the wavelengths where certain bonds absorb, it's really difficult when you see wave numbers to make those deductions. So people will probably ask you if you present in reflectance or wave numbers to rather just convert it to absorbance and wavelengths. So this is a typical NR spectrum of this looks like a whole wheat spectrum. And one way, and as you see, we get these broad bands because it comes from, we see combination bands, first and second, sometimes third and fourth overtones coming from the fundamental bands in the IR. Because of that, we get overlapping bands and quite broad bands. So this is why in NIR, we don't normally refer to these as peaks because we don't get sharp peaks. So we rather refer to absorbance bands. But if you apply second derivative, for example, and this is also something that Carl Norris suggested early on, he realized that you can understand or make the understanding of these complex, just wavy spectra much more feasible if you do derivatives. And here one can see reasonably clear what one can also call peaks or troughs in this case. So here you can see 4 clear troughs, which refer to moisture absorption. So these are typically 4 moisture peaks, which is easy to interpret in second derivative spectra. So as we know, all materials are made up of molecules, and they comprise of atoms. They joined by bonds, and typical bonds we'll see in agriculture and food products are the carbon, oxygen, hydrogen, nitrogen. And so the atomic groupings that we typically see in food and agriculture products are CH, NH, OH. So if there's a H absorbance, if there's a H in your compound, it's most, or your commodity, it most likely will absorb in the NIR region. But also because of these atomic structures of molecules, they are always in a constant state of vibration. So the vibrations or the frequencies of these vibrations are typical for each of these bonds. So CH, OH, NH will each have their own typical vibrations. And when the material is irradiated with something like light, they will jump to a higher level. And by measuring and that change, when this happens, you get that energy is absorbed. And by measuring this absorbance, it's possible to measure the amount of those molecules that's present in the material. So when you have, just coming back to the vibrations, the molecules or those bonds has their own characteristic vibrations. When it's scanned or light is shone onto that sample, and when the frequency of the light is similar to that of that specific bond, it will jump to a high level and you will get an absorbance. And that gives you an indication. So this typically will then be the bond where OH or NH, or the wavelength where OH or NH will absorb. And that will always be the case. And as I said, measured the reciprocal of absorbance, so NIR measured reflectance or transmittance, but we prefer to view it in absorbance. So this is basically the only chemistry I will explain is just the fact that the energy samples move to bonds move to a higher energy level, which allow the absorbance to take place. And these sort of jumps that they made to 1, 2, 3, 4 times higher are referred to the overtones. So these secondary absorbances are called then overtones from the fundamentals from which you can see in IR. So sometimes you find that there are 2 fundamental absorbers of the same molecular association close to each other in the mid-IR range, and they will then appear as combination bands. So again, broad bands. So you will then, from the fundamental, you'll get first overtone, second overtone, third or fourth. And it almost works as such that if the fundamental is at a certain wavelength, if you divide it by 2, you'll get to the first overtone divided by 3, the next overtone, and the next. You can, and what is interesting, so these overtones almost behaves like a dilution series. And because of that, we can analyze samples as is with NIR spectroscopy. So we can really, and that is one of the huge advantages of NIR, is that we do not really have to do sample preparation. And this is thanks to these, although it's weaker absorbances, but these weaker absorbances behaving like a dilution series allowed us to measure unabsorbed samples as is. Also because in the NIR region, there are so many of these bonds, you'll see NIR has many absorbers. And Phil really likes to do these sort of calculations. So I thought I'll include this. So he worked out that if a wheat kernel has 12% moisture and 12% protein, then it will have 1.2 times 1020 molecules of water and 1 times 1070 molecules of protein, and they all have absorbers and overtones. So it just shows how many absorbers you get in an NIR spectra. And it's with that Carl Norris started to develop second derivatives to help to interpret and resolve all these complicated assortments, and became the founder of NIR spectroscopy. Okay, so here we have, okay, are there any questions? I haven't had my eye on the chat. Any questions, or anybody wants to just add something, please feel free to just put up your hand or just switch your mic on and speak. I just want to mention quickly, I see Majid ask for you to fill the form, just for registration purposes. If you wouldn't mind, there's a link in the chat. So if you could just do that. Okay, get this out of the way. Sorry, let me just close this. Okay, so here let's look at some spectra. This is really important, is when you do NIR work, although it's really difficult to deduct information just by looking at the spectra. It's not like IR where you can really identify certain chemical bonds at certain peaks. You'll see here we indicated 1450 where moisture absorbed, but it's not always necessarily 4050. It can be anything from 1430 to 4050. Similarly, oil can range around 1725. Moisture can be anything from 1910 to 1940. Similarly, oil, you get 2310. There's also oil, I think this is 2320. But I just want to show you some spectra. So looking at the rooibos spectra, rooibos is a herbal tea from South Africa. When you look at the wheat spectrum and you look at the rooibos spectrum, there's not much difference between those. So it's really just wavy spectra. The only thing with the wheat spectrum, you might see a slightly bigger bond where more protein absorbed. When we look at, actually I should have included a moisture spectrum. A moisture spectrum will just give to, I don't know, could you see my arrow, or should I try and use a pointer? Can you see my arrow? Can you see the arrow? Okay.
Yes, we can see, Professor.
Yes.
Okay, thank you. So if I've had a moisture, if I scanned water, it would go like this with a huge moisture peak here and another moisture peak there. So you could clearly see that's moisture. Oil is also interesting because you can see the two very clear oil peaks at around 1700 nanometers and 2300 nanometers, clear oil peaks. And then it's interesting when you look at ground black pepper, it's almost similar to the rooibos, although pepper contains some oil. So you see some peaks here, 2310, and also broadband at 17, where there's obviously some oil. But why I want to show this is, again, because of the overtones. So you get combination bands, first overtones, second overtones, If you go further down, third and fourth overtones, and these, and you can see they become weaker as we go down in the wavelength range. And this is really ideal not to have to do sample preparation, and really ideal for quality control. And yeah, so once we have the spectrum, to make NIR work, to be able to use NIR effectively, we have to find that relationship between the absorbance values, which you get from your spectra at specific wavelengths, and the reference method to the reference values that you, or for the commodity that you would like to predict in future for with each of those wavelengths. So we need to find that relationship to be able to get a calibration model, which you can use in future. So here we see scatter plot of the added, okay, here one was added buckwheat, predicted buckwheat. So here was a model where we added buckwheat to a sample, properly to a wheat sample, and see could we predict that amount of buckwheat. And so this gives you an indication of how accurately you can do that. So important here to get this relationship to develop a model is, first, you really need good quality optical data. So your spectra must be of good quality. So it's always important, look at your spectra. It's easy not to do it because you collect spectra and you get it as a table, but it is really important to look at your spectra. Sometimes you find towards the end of the, where the detectors operate, some noisy spectra, so it might be necessary to remove some of those spectra. Important to have good quality spectra, important to have very accurate reference methods. Once you have, and from samples that has been well selected, and then chemometrics become vital, because what we have to do here is we have to extract that small portion of relevant information that will allow you to develop this model. So where spectra is the heart of the technology, the reference test is the heart of the application. So you can do NIR, just getting spectra, but you cannot really apply it unless you have a reference test or a commodity with some knowledge on it. The one where I like to explain how NIR works is, if we just, for example, this is a really old example of how people used to do Kaldal analysis, but when we do Kaldal or want to determine protein content, we have to go through a whole process of digestion, distillation, titration, where we have to extract the protein and then eventually measure the amount of protein. And then depending on the commodity, we would use a correction factor depending on how many nitrogens there are in the protein of that specific commodity, we can determine protein. So to be able to determine protein, we have to extract the nitrogen. With NIR, we analyze the entire sample. So we didn't measure protein, we measure wheat flour. So what we now have to do with the chemometric tools that we have to somehow extract that protein information to be able to predict for protein. So what we need to find is the spectra should be, in the first place, protein, nitrogen, NH should absorb within your spectra. And if you have samples that differs in protein, that absorption between the difference, or the absorptions at that wavelength between the different samples should be varied as such that it can be picked up for the calibration. So doing chemometrics, it really finds the wavelengths where that variation in relation to the commodity you want to measure is maximum, and based on that, the calibration is done. So we really need to extract that nitrogen information from the spectra, and that's where chemometrics is important. Often it's a really small proportion of relevant information, but it needs to find that. And this is just some examples of, this is typically some third and fourth overtones that you see in the shorter wavelength ranges. And there are tables that indicate, tables available that indicate what absorb at each of these wavelengths. And this has been done by people in the past where they would take samples, scan them, and then they would take pure samples of oil, protein, starch, water. In that way, they eventually identified what absorbed at each of those wavelengths. So so if you have need to interpret loading line plots or spectra, you can go to this table and get an idea what absorbs typically at those wavelengths. And typically also in the higher wavelength range, many more absorbers, where you again can see peaks where moisture will absorb. So the typical most important one would be 1410, 94. Protein is about 2100, well-known peak for moisture. And then oil is 2310, 2340. These are the two. And then 1724, 70 important peaks or bands where oil will absorb to help you to interpret your data later on. And there are tables like this available, which just gives you broad, just visually information where you can see where the different bonds would absorb moisture. You can see where alcohol, if you analyze alcohol, very specific alcohol peaks, CH3, CH, all the overtones, combinations are clearly indicated. This one is still in wave numbers. Okay, here they're giving the wave lengths in microns. Typically, we would report wavelengths in nanometers. Maybe I can just mention quickly before I forget, the reason why we get some instruments that work over wide wavelength range from 380 or 400 to 2500, where others only goes from 1700 to 2500 or even 700 to 780 to 1100. And that is often because of the cost of the detectors. So as soon as you go above 1700, you need more costly detectors. So some instruments stop at 1700, where so as soon as you want to go to 2500, the detectors do become more costly, and the detectors using in the wavelength, earlier wavelength range or shorter wavelength ranges are not as expensive. Okay. Okay, this is just to give you an idea of how does the pathways look when NIR absorb light. So if you have a sample, so this would be, say, for typical a whole wheat sample, you get your incident light C, so your light will go in, and then the light will be absorbed and reflected in different ways. So the one could be, which is not clearly indicated here, specular reflectance, which will just go straight back. And that would be if you have a shiny sample, so the light would just go straight back, you won't get any information from that. This one also just reflected away from the sample, no absorbance, and it misses the detector, so no information from that. Then you would get some diffuse reflectance. So the sample hits the sample, it's diffusely absorbed and reflect towards the detector. The same here, the sample. So it even scatters between the samples, but it will hit each sample, and some absorbance will take place, hit another sample, some absorbance will take place, and it will reach the detector. In this case, sometimes it scatters between the samples and it's scattered away, misses the detector. Whole grain samples, it will pass through the sample, absorbs through, hit different samples, short some small absorbances, and hit the detector. So we'll get diffuse reflectance that is collected by the detector. We get diffuse transmittance that's collected by the detector. But then there's transfuse transmittance that doesn't reach detectors. Similarly, diffuse reflectance that does not necessarily reach the detector, but you really aim to get maximum information from a sample once you've analyzed it. I just want to mention something about the texture of the sample. And again, I'm going to mostly refer to cereals. So if any of you have done some work on other commodities with similar experience, please just put up your hand and share with us. So we get the NR penetrates the surface, the cellular structure, and then it's irradiated. The material's being irradiated. Okay, so it hits the surface, the cellular structure of the materials that's been irradiated, and even the molecules themselves. So also if there's just a change in the molecule, NIR will pick that difference up. But the change of the surface of the material can change the reflectance and the energy that reach the detector. So that sometimes makes it possible to even measure physical changes. So if you get scattering from the surface of a wheat kernel, and as we've seen here, these are whole grain samples, and because there's some scattering from the surfaces of these kernels, also because they differ in texture, we get this wide vertical spread of the spectra. And this is purely by differences in the texture of the sample. So if we then apply a scatter correction method, such as multiplicative scatter correction that corrects for the scattering properties. So what multiplicative scatter correction does is it calculates an average spectrum, then it does a linear relation between, it does a regression between the sample spectrum and this mean spectrum. You calculate a intercept and bias, and then use that intercept and bias to calculate a corrected spectrum. So you use the mean spectrum, regress it with the sample spectrum, calculate a new bias and intercept, and then you calculate a new corrected spectrum. And then we get what we see at the bottom. So all those differences that we see in the top spectrum between the spectra was purely because of scattering. But what is now interesting, wheat texture differs, the difference in wheat texture relate to the hardness of the wheat. And wheat hardness is really important for the millers. So we sometimes want to measure the hardness. So if we do not remove that scattering, we can actually use that scattering information and predict the hardness of a wheat. So scattering is not always a bad thing. Nowadays, there are luckily pre-processing techniques to remove that information if it interferes with your measurement, but it can actually also be used as an actual measurement. Now I just have to see how far am I. Oh, I'm almost done. If we can just finish this, then we can stop for half an hour. So advantages, I know many of you have worked with NR, there's always the usual advantages that we list apart from easy and cheap to install, to operate. Some of the advantages also, I'll just highlight a few, is some of the standalone instruments not having any peripherals. So you have an instrument, it doesn't need a computer, it doesn't need a keyboard. It's just a simple instrument that you can use in industry that's easy to operate by the operators. Some of them are small in size. We now have handheld ones. The instruments are really durable. They can work for many, many years. It's safe to operate. The instrument's expensive, but once you have it and once you've calibrated it, the cost per set is easy. It says no sample preparation, but it sometimes does require milling or some level of sample preparation, but in many cases, no sample preparation. It's obviously fast. Importance is that the accuracy is equal to the reference testing, reproducibility often better, environmentally clean, flexible, and the fact that you can really measure a number of tests simultaneously. And then something which one often forget about, is if you work in a big company, is that you can have a number of instruments, all of them can be connected on a network, and you can operate them all from a single master instrument. Disadvantages: expensive. Lack of knowledge is often a problem, so people start using NR instruments. And I almost want to say the scary thing is once you have the instrument with the calibration, it will always give you an answer. Unless you know how to check that, how to moderate that, then it becomes dangerous. Then lack of knowledge becomes dangerous. So you will always get an answer, but you need to have a system in place how to check that that answer is always correct. You don't have to check all of them, but on a regular basis, you have to do that. You need separate calibrations for different commodities, although we found, say, for some cereals, triticale wheat are related to some extent, and we noticed we could use similar calibrations for those two. You have to monitor, you have to check your accuracy and precision of your calibration and your reference testing on a regular basis. You need to maintain those calibrations. You need to check your performance of your instruments. You need to check the diagnostics of your instrument. Yeah, and some people are still skeptic of NIR. They still don't think it could give a reliable result, but it actually can. So just a final word. So the contribution of technology, NIR technology, to the economy and the efficiency of industrial and commercial applications is really matched also by the contribution to a clean environment. No chemicals, but it really makes economical sense. So it does provide a cheap and effective method for analyzing things, and it just gives you so many options of different applications to try. Okay, I think that's an hour and a half, so I'm going to stop here. Thank you for now. I also want to ask, we're going to take, maybe if we can take a 25-minute break, if we can start again it's 11 my time, so in 25 minutes time. I'll be with you in a minute, Rumbi. Also, as we go through this, through the presentations, if anything pops up in your mind that you think you would like to learn more about, you would like more detail, if we can't cover it in this course, we can put it together and maybe sort of look at a further course to which we can easily with Zoom do. Sorry, Rumbi, you wanted to ask something?
Yes, Prof, I wanted to ask something. Can you hear me?
Yes, I can hear you.
Okay, I got a bit lost when you were talking about scatter and concentration, like on the hardness. May you please clarify for me what roughly the spectra should look like when you have different samples and they have different concentrations of something, let's say protein, or maybe it's the hardness. You really know that these samples have different hardness level. Roughly, how does the spectra look like?
Okay, sorry, let me just share this one again, which is now. Okay, so if you scan samples, that looks like the top slide, where you really see this vertical base, this vertical distribution. That typically means that the samples, each sample has a different scattering. So it scatters the light differently. And we know because if it's a powder, the powdered samples have different particle sizes. If it's whole kernels, the kernels also scatter the samples differently because of their texture on the surface, but also to some extent the texture of the endosperm. And that's why you would get that scattering. So if you get this for wheat samples, there's definitely some scattering, and there's likely to be, if their texture difference, there will be a difference in wheat hardness. But now we've corrected with multiplicative scatter correction. So we've removed the scatter as much as we could. And now if you look at the bottom spectrum, now you still see some differences. So you see some differences here at 1450. So that shows that there's likely also difference in moisture, because otherwise the spectra would have been more or less on top of each other. The same with 2100. Okay, where's my arrow? Okay, so where's my arrow? So here, you see there's still some differences there. So there's obviously some difference in moisture. The same here. Here you have, this is 2100. This is where protein absorbed. So there's still likely differences in protein. And similarly here, there's some fat in whole grain samples. So some oil peaks here, and this would be starch. So I hope that makes sense. So seeing such a wide distribution, I'll probably have another spectrum. If you have a powdered sample, let me just check. I want to know, wait a minute, the bottom one is a corrected one. The bottom one looks like flour. But if you have a powdered one, you get more separation to the multiplicative effect is more towards the higher wavelengths. But this distribution definitely indicates scattering and probably difference in hardness. Does it make sense now, Ruby?
Yes, it's now clear. I understand. Okay, thank you.
Yeah, so that broad spread typically refers to scattering and most likely difference in hardness in the case of wheat. And then once it's corrected for, you see there's still some differences, but then related to the compounds, the chemical differences. Okay, so thank you everybody for now. There's time to grab a cup of coffee. Nicolaus asked whether the presentation will be available. It will be available. Zikru, are you still here? Or Eran? Eran, have you joined us? Let me just check. Eran or Zikru should be able to tell us. I will get hold of them during the break, Nicholas, and they will explain to you where it will be made available. Okay, thank you everybody for time being. And if you have any questions in the meantime, suggestions for future training, please feel free as we go along to type it in the chat. I'll see you at 11 my time, 11 Turkish time, 10 South African time, 3, what is it? 4 o'clock Chile time. Emily, what time would it be in Chile?
Yeah, I think it'll be around 4.
4 o'clock in Chile. And we also have people from Kenya, I believe. Who's from Kenya? I'll speak to the Kenyan people afterwards just to check who joined us from Kenya. Okay, thank you, everybody. I'll see you in about 20 minutes. Thank you.
Thank you, Professor.
Okay, thank you so much. Thank you.
Thank you.
I just need to see that I have some more people already present. Okay, Zikru, Rasim, I can see. Radmila, hello. Hello, Kasim. Kasim is actually, I can hear Kasim from here, through here and from next door. Hello, Ege. Okay, who else? Typhoon is there. I just want to check, Ariel, are you now joined? I just want to check, are there anybody from Kenya that's joined us? If you can just indicate, please. I know some of them didn't get the Zoom link, so I just want to check that they're actually now online. So maybe while we're waiting for just checking, getting more people back, maybe somebody else can just introduce themselves. Who do we still have here? Anybody willing to speak? Yuan Wang, where are you from? Are you back yet? No, Miriam? I'm just calling a few names now to see who's here. Selene, are you here? No, I think Selene might be in the lab. And then we have Robert. Are you back? I think I'm still missing some people. Okay, we have Serap. Serap's here. Maybe you can introduce yourself quickly.
Hi, Marena. Good morning again. Thank you for this wonderful training school, first of all. I'm doing my PhD. I'm in the 3rd year of my PhD, and I'm working on the aerogels. I don't know, maybe you haven't heard it before. Aerogels. Aerogels is made by hydrogel, and evaporation of all the liquid in the hydrogel will be taken place, and then we will produce the aerogels. It's just a polymer structure, polymer skeleton, let's say, without any liquid inside it. And we produce them to use them in direct applications in food, like adsorption processes, let's say. And also I am using the HPLC and FTIR, and I am trying to discover the NIR, but it's really a new concept for me after the FTIR, because I mean, you mentioned the overtones at the last session, and it is interesting because I don't think that we don't have that much amount of overtones in FTIR, because the range in NIR is really high, and that's why I think we see that overtones. And before the training school, I thought that these overtones may be the disadvantage of the NIR, but now I see that it's really the advantage part of it. Thank you so much again.
Yeah, so the overtones, I know Phil Williams always explains it, if you take a stone and you throw it in the water, then it makes rings around it.
Yes.
So the first ring will be the first overtone, the second overtone, and they become weaker as they add more. And then if you throw two stones close together, where the stone would be the fundamental in the IR, so if you put two stones in the water, it makes those rings, and then they start overlapping, and that results in the combination bands. Yeah, so it is actually an advantage in NIR. It's an advantage, but at the same time, it makes the spectra really complex.
Yes, it's really challenging. Yeah.
But that then gives the chemometrics the chance to come up with these wonderful equations that can make it easier again.
Yes, now I see that. Thank you so much for this.
You're welcome. Yeah, again, any questions, or please feel free to just start speaking, or just switch your mic on and start speaking and interrupt me. That would be perfectly fine. I've put my email in the chat. If anybody wants to contact me afterwards for any reason, please feel free. So also welcome to Imran. Imran, I see you also here. Nice to see you here. Oh, there's Imran. Maybe you can introduce you quickly before we start.
Yes. My name is Imran Fakhr, and I'm ESR and PhD student from NIRS, Pakistan. Right now, I'm working on like sugar samples, like try to differentiate by using different analytical tools like NMR and like time domain NMR or fast speed cycling NMR. I recently, done my scanment in Serbia, and now I'm still working on my data. So we are still under, analyzing our data. So I think that's it.
Okay, thank you, Imran. I'm going, Zikru, I can't remember now. did I ask you to just explain to them where you're going to upload the webinars?
Yes, can you hear me?
Yes, yes.
Actually, after this webinar, we are going to share presentation and recordings, a Zoom recording on our webpage, and then we can mail you, or you can check the uploads from our webpage, which is SuChAQuality.com. So you can reach the materials and webinar information.
So, Zikru, where about on the website do they have to go and look?
Oh, let me leave the link into the chat box if you like.
Okay, maybe that might be easiest. Otherwise, they have to search through the whole website. Okay,
Yeah,
maybe
exactly.
Daria. Do I pronounce your name correctly? Maybe you want to introduce yourself quickly.
Yes, hi, my name is Daria. I am a PhD student at METÜ. I'm going to start my experiments soon. Thank you for your nice presentation, Dr. Marena.
Okay, thank you, Daria. It's good to see you all. Who else? Let's do one more in the top row. Racine.
Hello, everyone. First of all, thank you, Ms. Marena. It was a great presentation. We are waiting for continues. I am in the Middle East Technical University as a master's student in the first semester. I didn't choose my topic of thesis, but we will choose with Mr. Ostop, inshallah. Thank you again.
Okay. Thank you, Racine. Okay, so let's start with, I'll just upload my next slides. There's two, there we go. Okay, so I don't know if Rosario, if you're here, I'm going to start with just briefly, in my way, not being a chemometrician, not being a real spectroscopist, we're just applying NIR, explain some of the terms that we use to evaluate the NIR calibrations, and also just the introduction to chemometrics to maybe help it, make it easier. So the way I understand chemometrics in simple terms, and hopefully it will help everybody to understand what Rosario is going to, Professor Rosario is going to do later. So Rosario, if you're here, or anybody from University of Concepcion.
We are here, Marina.
Are you there? Great. So Rosario, as
yeah,
I do
Prof.
it.
Yes, Prof.
Are you all there?
Yes.
Yes,
Everybody.
Prof. I just got you now. Yeah.
Yeah. Oh, who's that? Ariel.
Ariel, yes.
Ariel, are you there? Okay, sorry. Ariel, I'm glad you're here. If anybody else from Kenya, if you know of anybody else who didn't get the link, please forward to them. And as
I just sent it to Dr. Irene. She will be joining soon.
Okay, that'll be great. But the session that you've missed, Zikrula just explained, it will be uploaded on the SuChAQuality website, so you will be able to look at that afterwards. So I'm sorry that you've missed this, but great to have. Yeah, great to have you, Ariel. Yeah. So Rosario, as I explained, if you want to, please interrupt at some point. If you want just to elaborate a bit more on my simple explanations, I'll be more than happy, so that they really can get the best and the correct information. Okay, so we're still busy with the practical implementation and the use of NIR spectroscopy, application of NIR spectroscopy. And as I said, my focus is made mostly on serials, but I'm sure those of you already doing NIR should be able to, in your mind, also see the application for the commodity that you work on. So again, I'm doing this in association with Dr. Phil Williams. And I must say I've reorganized the modules to some extent so that I could cover this part before Professor Rosario started in the afternoon. So we're going to this session, module 2. I'm just going to look at some of the statistical terms that we use to evaluate the accuracy and precision of NIR spectroscopy. So when we start working with NIR, we have typically observations, sometimes referred to it as objects. So that would be the individual item of data. So that is your actually sample. So your observations is your sample for which you will have for all practical purpose now speak of absorbance. You will have an absorbance value for each of those. The population then would, so the observation is for a single sample, or object would be a single sample. Population would then be your total number of observation or all your samples. So, and then just to sort of make it clear how we use the terminology in NIR and NIR software. So when we talk about the calibration equation, we tend to use the term model or calibration model. So when they just speak about models, it's actually the calibration equation that you've developed for a specific application. So when we work with NIR, there are two types of populations often. So if you work in industry, the population or your would be just whatever is available. So you will just, within the environment that you work, just start collecting samples, whether it's bags of flour. If you work in a breeding program, it will just be bags of wheat. If you work in any other industry, it might just be all the ingredients coming in. So you really take what is available. On the other hand, and that's more likely to happen in research, is if you want to test something specific, then you would collect samples specific to that application. So for example, we did some work on maize hardness at some point and how it affects milling quality. So then we would go to the wheat breeders and ask them, please give us a range of maize samples that differs in hardness so that we can get a good range on which we could then measure the milling quality and use it as such. Or I'm just thinking now in terms of what Typhoon is doing, where he wanted to measure ascorbic acid. And this is something that's not often done, but in this case, it could be useful as he actually prepared his own samples. So he prepared samples with different levels of ascorbic acid. And but this is interesting. So we would in industry develop a calibration to help you to do routine analysis. In research, we often do development work to develop applications for a specific commodity that becomes our research project. Typhoon is doing something interesting. He's got a completely different project. He wants to evaluate something, and he's now developing NIR calibration to assist with his project. So the NIR is not his main work, but it actually he hopes that would become a tool to do his research more effectively. So we can get different populations, different ways and means to collect samples. I just want to say something again about the population if you collect samples from industry. When you work in industry, say you have ingredients, the disadvantage is that, say you want to measure protein in flour. So if you always use the same flour, the protein will always be the same. But to develop a calibration, you really need a range of protein contents. You can imagine you cannot do effective calibration if all your samples just got the same content. So this makes it difficult to develop calibrations in industry. So there you somehow need to collect samples in a different manner to cover a wider range so that you could do effective calibration. When you collect samples as part of a research project, then you can make the effort to collect samples of a wider range. So the success of any exercise, NIR exercise, really depends on the selection of your samples. It is crucial, and it is probably the most difficult part. It often is, unless you work in an environment where, if you work in a breeding environment, there's just a huge number of samples with wide range of analysis. So that makes it easy, but in some cases, it's not that easy to collect the samples. So the success definitely depends on how well you've selected your sample, and the practical application will then rely on what's the results of your statistical analysis, again, sample selection. Also important is how you've assembled your sample and how you actually present it to your instrument. We actually looked at examples of Honey yesterday, where he tried to analyze a tablet, a large tablet, and then we realized that the tablet did not fit well into the sample holder, and that might have affected his results. So NIR seems to be so easy. You just put the sample down, you scan it, but just that sample, because it didn't fit, was not always maybe evenly put down on the sample holder, and that could have affected these results. So sample assembly, sample presentation is important. So it's easy to do, but it's really important to always do it in a consistent way. You always really want to do something as consistently as possible. So we have, as you all would know, we work with independent and dependent variables. So with NIR, our independent variable would be on the x-axis, your independent variable on the y-axis. And when you develop your NIR calibration, during that stage, your spectra would be on the x-axis. That would be your independent variable. The reference would be on the dependent variable, would be the dependent variable. When you compare predicted results to reference results, then your actual data or the reference data will be on the x-axis, your independent variables, where predicted results will be dependent on the y-axis. And then again, when you predict in routine analysis, your spectral data become your independent variables again, and the predicted data, your y variables. So within our spectra, when we predict our results or evaluate the predicted results, so this is, once you've developed a calibration, you need to test it. So we know the values of the samples because we did it. So we say, I always talk about protein in wheat because that's what I grew up with. So you measure protein in wheat, we know what it was, we predicted it with our model that we've developed, and this gives us indication of the accuracy of our model. From this data, we can calculate R-squared, which we'll get to in a minute. We can calculate your prediction error, but this would be typically a plot when I present or publish NIR work. The first thing, you make sure that you actually show spectra in your paper, and the next thing would be to show reference against predicted scatter plots, because that gives you a pretty good idea how well your data fits on the 45 degrees line. So this is just repeat, depending on whether you develop a model, evaluate, or routine analysis, your independent and dependent variable will differ. So important that we mostly will see plotted is the evaluating the model when your reference data is against your predicted data. Okay, so what are the statistics that we would typically look at? I'll cover a few here. This actually, you can see there's loads of them. I'll cover some in a bit more detail, and I'm sure Professor Rosario will also refer to this in much more detail when she presents the section on chemometrics. So the first three, mean, median, standard deviation, is always important, whether you look at your spectral data or your reference data. It's always useful to determine, for example, a standard error of a single test, where you can just repeat the same sample 10 times, calculate the mean standard deviation to see how much your samples differ. The mean and the median, if you have a normal distributed samples, your mean and median will be pretty much similar, but those basic information or basic equations that you all should be familiar with. When you present NIR data, it's important to also report the range of the reference data, because you need a range as wide as possible. So if I measure protein, I ideally want, say, 9 to 18. So you want a wide range. So you would typically report the range. And a good thing to do is to present those results in a histogram, because then you see what you really want for NIR. Say I have proteins from 9 to 18. I want an equal number of samples for all those ranges. So you don't really want a normal distribution. You almost want a block of data. So you want equal number of samples with 9%, 12%, 18% protein. But that is really difficult to obtain in real life. So if you start collecting samples, you will always see towards the end that you have a normal distribution, which is likely to happen. So if you have lots of samples, you could actually not necessarily use some of the samples that's sort of towards the center of the distribution, because that might not really contribute to your calibration. So if that's going to add cost in terms of reference method, you could actually remove some of those samples. But important to report the range and show it as a histogram, because then you really can see the distribution of your samples. Okay, standard deviation we've mentioned. Coefficient of variance is useful when you want to compare two sets of data. The bias is important because that shows you the mean difference between your actual results and your predicted results. So then you see, sometimes you see, it seems like you're predicting accurately, but you always predict either 1% too low or 1% too high. If that's the case, you can make a correction. Correlation of coefficient, you see a correlation. More importantly is the coefficient of determination, which explains the amount of variance explained by your equation. So the coefficient determination is the better term to acknowledge. Regression coefficient, the slope and intercept, that's important. When you really see a slope in your data, then it might mean it needs, in most cases, it might need to be recalibrated. A small slope, you might be able to correct for that. And then the differences, distribution of differences between the near-infrared predicted and the reference data, that's your residuals. It's also important to look at the distribution of those residuals, because if you see the residual means is how incorrect or correct your sample was. So if you see small residuals at the lower end of the wave of the prediction values and large residuals towards the end, then you know something is wrong. So you really want a random distribution of those residuals. Then you can determine the error of a single test, as I explained earlier, 10 measurements, calculate standard deviation, see how they differ. Standard error of laboratory is important. I will show an equation later where you can actually, for your specific test of samples, where you would use your validation set results, and you can calculate the error of your laboratory. And then you can compare your NIR prediction with this result, because you want that to be as close as possible. Standard error of performance shows how well your calibration performed. I'll explain where we use standard error of cross-validation in a minute. You can determine the root mean square deviation. True test error, similar to your error of the single test. And then two terms that's often used. The last one, maybe not as much, but the RPD is also something that for Williams developed. And that's the ratio of the standard deviation of the validation set to the standard error of prediction. And what this does, it removes the units from the prediction result so that you can really compare different calibrations. So, and that we'll come back to that later as well. I've included two papers here. I must admit the top one I couldn't find yesterday, but I will look for it again. This was a paper in NR News, which Pierre Dardenne wrote. And he just indicated when you report on NIR work, what should be the typical parameters that you should include in your report with explanations on that. And then together with Phil Williams and Peter Flynn, they wrote a paper for Journal of NR Spectroscopy, where they wrote a more detailed tutorial on items to be included in the report on an NIRS project. And some of those terms are also well explained in that paper. If you can't get hold of it, let me know and I can forward it to you. I can maybe ask Zikru to maybe also upload that. And that is a really useful paper when you're new in NIR and you want to write a paper, just to advise you or maybe guide you to some extent that you really include the useful parameters that should be included when you report on NIR work. Okay, the mean is something that I don't need to explain to any of you, that you all should be able to do, but Phil likes doing everything in detail to make sure everybody understands, so you can calculate the mean difference. Okay, and as we know, the median is the center value, which if this would have been a normal distribution, it would have been similar to the mean. Okay, then the standard deviation, which expresses the variance in a set of data, and that really helps us to understand. So we can look at the variance in your spectral data as well as the variance in your prediction data. So that can be calculated for both. So we can calculate standard deviation for X, which is the spectral data, and the standard deviation for Y, which is our reference data. I want to say something else. Okay, yes, so that's standard deviation. So how to calculate the standard deviation. And a small standard deviation means that the values are really close to each other. A large standard deviation means that the data are set far apart. When you calculate the standard deviation of your data set that you want to use in NIR, we really want that standard deviation to be large. You don't, if you have a really small standard deviation, you're going to find that you're not going to get a good calibration. So you really want a standard deviation where the values in the data set are far away from the mean on average. So this is important. So we really want a range of data. Also, just something else to mention. So standard deviation, typically 1 time standard deviation would typically mean, okay, in the previous case, it's been calculated as 2.18. So the value of 2.18 would means that it only represents 67% of the data. So it's always better to do, we typically would use the 1.96, which represents the 95% of the population, and we refer to that as the 95% confidence limit. If you use that or 2 times the standard deviation, which represents, or 2.56 times the standard deviation, which represents 98, there's still data that falls outside your population. But it's important to also include that data into your calibration set, because they're not outliers. It might seem, because it's only a few of them, that they're outliers. It's important to also include those samples into your data set. Yes, yeah, so this is what I've just explained. So, for example, if you have a population of 500, which is a good number of samples if you develop a calibration, you will find that about 10 samples will be greater than that 2.56 times the standard deviation. So they will be situated here. But it's important to also include that 10 samples. It should not be deleted as outliers, unless there's a really good reason for that. But ideally, they should also be included. Okay, coefficient of variation. That relates the standard deviation to the mean, expressed as a percentage. And this is a useful statistics if you want to compare the degree of variation from one set of data to another set. Even if the means differ completely, it still helps you to compare 2 data sets. And this is just in step by step if you want to calculate it by yourself. So you can calculate the coefficient of variation. When we interpret that, we really ideally want it to be as low as possible. So if you work with reference data, it will most likely be quite low. If you analyze a series of samples, it would be 0.5 to 1. That would be really exceptional results. When it comes to NIR, predicting protein, we find that it will be seldom that we get such low correlation of coefficient values. And even when we predict like functionality, which is not content, where you predict, for example, gluten development, it will be slightly more difficult to get those low coefficients of variation. And they will probably be, if you get a 2 to 3%, which would be exceptional. It's interesting that when you report, you'll see those papers reporting coefficient of variation. You don't often, reporting NIR results, you don't often see people reporting the coefficient of variation. So something to consider. Then two measurements that should receive attention is repeatability and reproducibility. So repeatability is if the same person, same instrument, just repeat analysis over and over again, which will in most cases be quite low. And then the reproducibility is where you really try to reproduce the entire experiment on its own, not necessarily by the same person, and that will usually be higher. So if we do a test, if we run 12 tests, repeatability, same person, no, very little variation, you'll see that the standard deviation will be much lower than when we repeated the experiment, say by more than one person, or repeated the entire experiment from scratch, including collecting samples. So repeatability and reproducibility is also important to evaluate each time when you do a new application. The bias, this is calculated from the NIRS predictions, that was in the test set or the validation set in relation to the reference data. So once you've developed a calibration, you now take your actual values, you predicted your new samples, and then see how well those data fit on the line. So if there is sometimes likely to be a bias, and that's the mean difference between the reference and the NIRS data. So it really measures the overall accuracy of the calibration. So that is now relative to the reference method. So you can calculate the bias where you take both the Y, which is your actual values, and the Y hat, which is your prediction values. So Y and Y hat is often used. Okay, we've seen earlier, X usually refers to the spectral data, Y refers to the reference data, where Y is your actual data, which you've measured, and Y hat would be your predicted rate value. So a bias can be positive or negative, and the bias is something, if it's not too large, that you could actually make a correction. So if you see a bias in your calibration, so say you have a calibration that works really well this year, next year you start using it with new samples, suddenly the result shows a bias. And you could then, if it's not too big a bias, make that correction. If all the samples measure 1% too low, you can make that correction to adjust your calibration to make sure that it would now predict the accurate results. So this would be typically what you would see if there's a bias in your data. So the data seems to be well predicted, except it just does not fit on your 45% line or 45 degrees line. So this could be that all these results are more or less 2% lower to what it should be. So you can adjust your calibration so that when you predict it again, all these samples will lie on the line and you will get accurate prediction. So it's possible to correct for bias. So you can, even when your SEP is low and your R-square indicate that you have a very good calibration, there could still be a bias. And this is important. For example, if you, I'm back at protein for wheat farmers, if the farmers get paid a premium for a protein content of 13%, we use a calibration at the silos. It predicts 2% too low, so it predicts 11, that farmer will not receive its premium. So it will be really costly for that farmer. So it is important, if that bias exists, to correct for that. Similarly, if you measure 13%, which is too high, then the people paying will be losing money. So in the world of commerce, if there are bias and premiums are paid, it is really, really important to make sure that such measurements is correct and the biases has been taken in consideration. Okay, correlation coefficient, you all should be familiar with. It just shows the degree to which two sets of data agree with each other. And here we've given the long explanation if you want to calculate it by yourself. And also and then the coefficient of determination, which is always the better term to report when you do NIR work, which shows the proportion of the variance in the Y that has been attributable to the variance in the X. So the proportion of the variance in your reference data that is attributable to the variance in the spectral data. So if you have an R value of 0.97, it will give an R square of 0.94, always slightly lower than your R square. So an R square of 0.94 means that that percentage, 94% of the variance in Y, can be attributed to the variance in the spectral data. And then that 5.9% is attributable to any other factors, whether it's noise or sampling or whatever the case was. Errors, and R square is usually positive. So the larger your R square, the more variance in the Y has been well predicted from or explained in your spectral data. And that's really what you would like to see. And again, you use the difference between your actual values that you've measured, the reference data, and the predicted data. So you use that difference between reference, predicted, squared, summed for all the samples, divided by similar for all this, divided by the average. Y hat is the predicted values, Y with the line is your average reference method, reference result. And 1 minus all of that will give you your R square. So if you want to calculate it yourself. I know normally you just press a button and the software just pops all these results out, but this is just to give you an indication how it's actually calculated. And R is always positive. So if you have a perfect agreement between your X and your Y, spectral and reference data, you will get an R square of 1. R and R square of 1. But in practice, this is seldom that you would get this because there's usually errors in both X and Y. It's seldom to get everything perfect. But how would we interpret this in terms of NIR results? So if you get, let's look at R square, because that's really what we will report. So R square up to 0.25, not really usable. Up to 4.9, still not ideal. When you get to 64, you can start using for rough screening. 0.8, that's for screening. You can start doing screening. And it's often already useful with NIR if you could do just some screening of the samples. So by doing some screening, you can remove extremes. And if you still have to do reference methods, at least you can reduce the load of the reference methods that needs, or analytical methods that needs to be done. When it gets to up to 0.9, they still say use with caution, and it's only really when you get R squares of 0.96 that is usable in most applications. And then obviously 9.98 upwards, it's really excellent. And working with biological samples, it is really hard to get really good calibrations all the time. So sometimes it is disheartening if you really work hard and you end up with R squares of 0.5 or 0.6. So it is often disappointing. So then one have to try and figure out why and can you improve on that. But this is just to help you to interpret those results once you've done that. And just to give you some indication of what these lines would look like. So if you have a really good, okay, this is now, this is now given an R, so the R square would be slightly lower. So with the R, you get the first one, a high R, almost all the lines, the data points fit quite well on the 45 degrees line, 4.99. Still some of them on the line, but some a little bit away from the line. When you get to 0.95, you can see the sample's not so close to the 45 degrees line, and for a calibration with the R of 0.85, even more distributed. And this is often more likely what you will see with some biological samples. It is, and especially if you really want to make sure that you want a robust model. So you wouldn't necessarily get a perfect prediction, but it does happen at times. I just want to check if there's any, okay. Sorry, I just want to check, I saw there's something in the chat. If there's anything I need to pay attention to, please just let me know. Let me see where now. Okay, so that's just typical what you could see when you plot your scatter plot of your actual versus predicted results. Okay, so the regression coefficient, which also refers to as the slope, and the intercept, that also show a degree to which values of y can be predicted from those of x, from x. The regression coefficient and the intercept can be positive or negative. Again, we've given the longhand equation if you want to calculate yourself. So if the ideal slope should be, the ideal slope that will assume no error should be 1. So ideally you will like a slope of 1 and the intercept of 0. This is possible, it can happen, but it doesn't necessarily happen all the time. So you often get small differences in slope, in your intercept, and sometimes together with bias. And if there are small differences, you could correct with bias adjustment. In practice, bias adjustment is more commonly. Slope adjustments are rarely recommended because if you do a slope adjustment, if you have a data set and you want it to work better, you make a slope adjustment, then it will work for that data set. But as soon as you start doing new samples, it might not work well again. So slope adjustments is not ideal. It can be maybe done once, but you shouldn't continuously do slope adjustment. And just to say that you should not confuse the intercept from the bias. The bias is like this distribution of the whole set of samples, the intercept where it sort of cuts the Y line. Again, just some examples. So to the left, you see a bias in your calibration, which could potentially be corrected for. And to the right, you see a prediction results, which would, if you want to fix it, you might need to do a slope correction. And I must admit, I haven't done this for a long time. So I was thinking the other day, I couldn't remember exactly how one would go about doing a slope correction. So maybe this is something that Rosario can cover with you if she has time this afternoon or tomorrow. So this might be necessary, but just be aware that a slope correction is not ideal for a long-term fixing of a problem. Yeah, so if your slope is really just a small 0.05, then a slope adjustment will not really make a huge difference. But if it's greater, if the slope is really large, that means that your calibration will really not be stable. So in the end, it might be better to rather just redevelop than trying to correct for the slope. So, and typically you would notice a slope when you start analyzing new samples. So then what you would ideally do is those new set of samples which you've analyzed, which now show the slope in your results, is get the reference results on those, or you would have the reference results on those samples, is to incorporate those samples into your calibration and recalibrate. And yeah, this is just sort of a few lines just to show what can actually sometimes happen. So you can get this perfect, the gold line is your 45 degrees line. So you can either get, that would give you an ideal slope of 1, intercept of 0. So you can get this line, which shows some level of some slope, a negative intercept, positive intercept, and again, quite a large slope. So, sorry, just want to show you this result. So if you get a line such as the gold line, perfect slope, then you know values, the low values will be accurately predicted, and the high values will be accurately predicted. If you have like the green line, where you have a high intercept with the slope, you'll find with this line that the low numbers, the low reference numbers will be predicted too high, and the high reference numbers will be predicted too low. So you cannot just correct with a bias, because some of the numbers will be predicted too low, the others will be predicted too high. Similarly, the line number 7, where the low reference numbers will be predicted too low and the high numbers will be predicted way too high. So again, you cannot just correct this with a bias correction, but this is dangerous and one needs to look at this. And this is why it's important to monitor your calibrations. I cannot remember if I said it earlier today or who I said it to, is the dangerous thing with NIR. If you do this, it will always give you a number. You will always, when you apply NIR, you will always get a result, and you can always use that. So if you just use this calibration, you will get results. You will just believe that. So unless you monitor and check, you would not realize that some of these results are too high or too low. So that's why you really need to do regular monitoring of your results or of your calibration. Okay, then the standard error of a single test, that's just the reproducibility of the test, either by reference or NIR. So you will just analyze the number of tests and calculate the standard deviation. So that is really important to make sure that you can do repeatable or reproducible analysis. And it's important, I know NIR is really simple, but to present results in a consistent manner to the instrument is really important. And it's something really simple. If you have a Petri dish that needs to be filled with whole grain, if you fill it sometimes from a low distance, high distance, medium distance, you pack it differently. So the ideal is always fill from the same distance. If you have a Petri dish, maybe even filled with powder, tap it maybe once, just drop it, tap it once on the desk, on the laboratory surface, scrape it off always in a consistent way. So it is really important to do your sample presentation in as consistent way as possible. And that's why it's important to check this reproducibility. So the first time that you do NIR, just test the way you present your samples and make sure that you can do it in a consistent way. So you check your, similarly, when you do reference methods, check your reference method 10 times, 11 times, calculate standard deviation, see if you can do it accurately, same for your spectral data. Then the standard error of laboratory. This is the equation that we've been used for a very long time. So what we do is we calculate the laboratory error, not for the sample in general, but for the analysis that we have for our specific data set. So we will deduct the, so this you can do when you have duplicate analysis. So our reference test we would normally do in duplicate, and by deducting these two from each other, square for all of the samples, add it up, divided by 2 times n, and the square root of that will give you your standard error of laboratory. And you will always aim for the standard error of laboratory that your standard error of prediction should ideally not be more than 2 times the standard error of laboratory, or even better, 1.5 times the standard error of laboratory. We have found that, say, for example, if you use HPLC methods that's really accurate, that it is difficult to get to that type of accuracy when you do and when you compare the SEP, the standard error of prediction, to your standard error of laboratory. But standard error of laboratory is important to measure. It's important to include in your when you write papers on NIRS, because then the reviewers or the people who read it have some idea whether an error is acceptable error or not, because there's no rules saying what the SEP should be or should not be if you only look at the SEP as such. Then the standard error of prediction, or your RMSEP, that's your standard deviation of the differences between the reference and the NIR result. And here you calculate yourself. And in this case, you see it could take the bias in consideration. So it corrects for bias in your equation. So the standard error of prediction indicates, give your SEP, and it's this SEP that we always relate to our SEL. Also important, your SEP should be measured from the results of a prediction set that was not included in the calibration model. And there's now different ways of means of doing this. So what we would typically do is you would have a population, because again, we're not always all spoiled with too many samples. So say you have a population of 100, then we will use certain technologies or techniques to separate 20 or 30% of that sample, take that from that population, and then you're left, let's say, with 70 samples, and that 70 samples you will use to develop your calibration. And I believe Professor Rosario might cover this. There are simple ways to select these two sets. There are also more the techniques like duplex or Kenneth Stone that you can use, and that really helps you to select a set that the distribution within both sets are similar and that the validation set fit within the calibration set. So you have a calibration set and you test a set of samples that has similar distribution, but within, it fits within. So the larger values will be in a calibration set. So when you do your calibration, you will use what we refer to as cross-validation, and then you get your prediction value as a standard error of cross-validation. So what cross-validation does is, if you use, we refer to it as leave one out. So you have your sample set, we take one sample out, we do the calibration, and then we predict that one sample. And then we put it back, take another sample out, do the calibration, predict that sample, and put it back. So in that way, we've developed a calibration, and we've actually tested all of those samples independently because they weren't part of the calibration. So that gives you your first indication of how well your calibration would work. And this is then typically the set of samples that we will use to determine the number of factors that we will use in the calibration. And once you've done that, I'll get back to this a little bit later, and I know Professor Rosario will also explain this in detail. So once you've done that, now you can take your calibration, use that number of factors. So say we use 9 factors, and now we predict a separate, that validation set that we've taken out. And that set would give you the standard error of prediction. So some people will even call it the standard error of validation, and then they will get a completely new data set to do this, to test it again. So you would call it, so typically you would have your calibration set where you test with cross-validation and you get a standard error of cross-validation, and then you can get tested on the set that you've removed, your validation set, and you will get a standard error of prediction. And that prediction, as I said earlier, should ideally not be more than 2 times your standard error of laboratory, and ideally, well, at least not more than 1.5 times your standard error of laboratory. But we'll come back to that a little bit later. I just want to check now whether I've set this properly. Yeah. Okay, standard error prediction, but some people want to call it standard error validation. But what we normally see in papers is that they use the SEP or the root mean square error of prediction, the RMSEP. But I'm sure Professor Rosario will explain this in more detail when she does the calibrations tomorrow. This is just to give you a brief overview. So this is just something interesting to test. Sometimes you find that your SEP and your R-square values do not look very good. So this is now when you've developed a calibration using cross-validation, you use the number of factors, you predicted your independent test set or validation set, you've got to ask SEP, and your R-square and your SEP still do not look good. So that means your standard deviation of differences between these two results is just too large. So what you then could do, and this is something that Phil suggested, is then do a calibration without standard error of cross-validation and just predict. You do a calibration, you predict the same samples again. And if there are obvious outliers, they're likely to pop up then. So you won't do this normally because you predict the same samples that you're calibrated with. But if there's a mistake somehow in either your reference methods or a spectrum that didn't scan properly, those outliers will pop up when you do that. So that's maybe just a tip to look at when you get to that. Okay, RPD, this is something that Phil designed. So this is standard deviation of your prediction, your validation set divided by your standard error of prediction, or in the case if you want to check it for the cross-validation, you can do so. And this is why I said you want this number as large as possible. So if your standard deviation of your calibration set is really small, you will get a really low RPD. And if your SEP is slightly bigger, you will get a really low RPD. So the larger your standard deviation, the smaller your SEP, the better your RPD. The REE is seldom used. It looks at the range in the compositional data, maximum minus the minimum divided by the SEP, and that gives a much larger value. It gives an inflated value, so it's not used as much as the RPD. But when you look at the RPD, you're really looking for values at least of 5. And you find for some biological samples, you seldom get above 3, but 5 and higher is really what you're looking for to have something that would be useful in quality control or process control. So just finally, the SEP and the bias together describe your overall accuracy of your test procedure. You can use the RPD, which relates the SP to the standard deviation of the reference method. And that also takes away the units. So that with the RPD, you can really compare different methods. R-square indicates the closest fit. How well does your NR data and your reference data fit each other? And just a useful guideline is to have 25 samples for every wavelength. So that's if you work with a filter instrument that only has specific wavelengths, you will have 25 samples for each of those. Or that's now if you use multiple linear regression, or if you use, for example, PLS regression, the guideline is at least 15 samples per factor. Or if you have, sometimes you wanted to do it the other way around. If you have so many samples, you divide it by 15, then you should be careful not to use more than that number of factors, or it might be overfitting. Just the last thing before I forget is standard error of prediction, standard error of cross-validation has units. So please do not forget to include the units. So if you measure protein percentage, then your standard error of prediction will have percentage as a unit. And people often forget to add the units to their error terms. So just please remember that. Okay, that was quickly, wasn't that quickly? I see it's already an hour and I still have about 100 slides. So let's see, we can do 100 slides in half an hour. Any questions or comments or suggestions by anybody while I open my next slide? Please feel free to say anything or type in the chat or just ask. Sorry, let me just find the other presentation. Sorry, I've lost my presentation. presentations now. 1, 2, 3. Sorry, where's 3? Okay. Just share. If there's no comments, questions, anything urgent, then I'll continue. Aleph, you okay? Yes. At least I have Aleph in my office, so I can ask her. So if there's no, everything okay? Okay. Rosario, I think they're going to have all the questions for you coming from my presentation this afternoon. Okay, sorry, have I shared? Yes. Sorry, can I just fix this typo, which I saw yesterday? Okay, so this is now something that I think it's about 100 slides, but I see how quickly I can go through it. And this is really, again, my attempt of explaining basic chemometrics in a really easy way. So, and which for those who've never worked with chemometrics will hopefully help to understand what Prof. Rosario will do this afternoon a bit better. So I'm going to just briefly introduce you to some NIR software and then just some really, really basic chemometrics. And I'll try and do it quite quickly now. So if I go too fast at some point, please just stop me. I'll just see if there's somebody in the chat. Yes, okay. Prof. Rosario says she'll be happy to answer all questions coming her way this afternoon. Thank you, Rosario. Okay, sorry, let me just get my slides. Where am I? Okay, so the NIR instruments that we use, they often how we use them, some of you being at university, you will be familiar with the instrument sitting in the laboratory and you can just use it whichever way you want and for whatever application. But some instruments are actually in a factory, so they can be standalone when samples is collected and they are analyzed in the laboratory. They can actually stand next to the line in the factory, or they can be online. So these type of instruments are usually calibrated by the manufacturer, sometimes with input from the supplier, and they would just run. So those instruments would be the ones where you will bring in that maintenance plan that I showed in the beginning to check that regularly. So the software that's used for NIR instrumentation, typically we have dedicated software that's supplied by the instrument manufacturer, and then we have generic software. So the dedicated software, for example, with the Buchi, we have a Buchi in Stellenbosch. I know here at Metu, they also have a Buchi. So there you would have the Is software. So what the Is software does, you need that to run the instrument and collect the spectra. And once you have the spectra, you will export it to NIRCal, which is a separate software package where you will do your calibration. And similarly, you have Opus for Bruker, One Eyes, iVision. You have the different software for the different manufacturing instrument manufacturers. So this software, as I said, with some of it will be used for recording of the spectra. Some is used for the calibration development, and then you might, and for the operation day-to-day to determine diagnostics, and there might even be separate software to do the networking if you have a network of instruments. The generic software, that would be software such as, for example, Unscrambler, which is quite easy to use. I've recently been introduced by Hibli to Orange, which I find a really interesting way of analyzing data. And then obviously people who are familiar with coding, they use MATLAB. And to make NIR analysis easier, you can use PLS Toolbox, which is supplied by Eigenvector, which is really a really effective way of using some MATLAB coding together with PLS Toolbox to do the operations. And if I'm not misunderstood, they now also have a toolbox for imaging, for people doing imaging analysis. So the benefit of the dedicated software is once you've calibrated your done your calibration, it's really easy to set the calibration in the instrument. With generic software, you first have to export, and then you somehow have to get that model set into the instrument software to be able to use that effectively. So that's would just be slightly more cumbersome to do. But we find that using Unscrambler MATLAB sometimes just gives you a bit more flexibility in what you do, and also the option to try for chemometrics newly developed algorithms. What the dedicated software sometimes does is, I think I mentioned it earlier, they have these wizards, so you can really run a calibration with the help of a wizard. So if you're really new to NIR, it helps you just getting through the process initially, but it's important to then make sure that you really understood how the wizard's gone about it, and the results you get, whether that's the best results, or then maybe take that results and evaluate that further and maybe test some more. So the purpose of the software is obviously instrument setup, standardization. This is just something when manufacturers have different instruments, you cannot necessarily use the same calibration on all the instruments, because it's really difficult to manufacture identical instruments. So they also would have software and means to standardize the instruments as such, so that when you use the calibrations, they would give the same results. So standardization is another part of chemometrics or instrumentation, NIR, that you really need to master if you use a number of instruments. Record the spectra, and then during dating handling, you have to make sure you have an option. You can view your spectra, you can add IDs, you can add reference methods, you can average spectra, your file setup, and sometimes there are compatibility. I must say, like Unscrambler, a lot of the software or dedicated software allow you to export your results, so that can be opened in a number, like opened in MATLAB and Unscrambler in a range of other software as well. So within the software, you then obviously do your mathematical treatment, your pre-processing, calibration, discriminant analysis, if that's what you're interested in. I haven't really mentioned that, but I know Prof. Rosario will do more on discriminant analysis, and obviously validation, prediction, any corrections if necessary, apply remover. Some companies use a series of instruments. If you have a number of flour mills, you will have an instrument in every flour mill. So those instruments need to be able to speak to each other. So you will have a master instrument. So if you want to make a change, you can really from a single computer communicate to all those instruments and update them and add information. Some of the dedicated software obviously will have your instrument diagnostics, it will have special graphics, and it actually has means of generating reports for clients, which is really great. And also some of the instruments would speak to a laboratory system. So if you have a laboratory system in your laboratory to collect data for reports, some of the software also allow you to do that. I just want to mention this, when you record spectra, there's really a number of things that you need to look at. So you will create data files in which your spectra will be stored. So a spectrum is actually, a number of spectra is just a table. But sometimes you need to set up the instrument to accept the spectral data. So you sometimes have to sort of like start an app, or you have to start a project where your data can be collected and stored. What is important, a number of things that you often have to do. When you scan NIR data, you would typically scan, it will be one sample, but it will be scanned a number of times. And typically you will scan up to 100, you will do up to 100 scans. So some samples will rotate. So it will be a Petri dish that rotates, and as it rotates, you will scan it about 100 times. And you can set that number of scans. Just remember, the more scans, the longer it will take. But if you don't scan enough samples, your spectra will be noisy. So this is one way of get rid of too much noise in your spectra. When you work with the FT-NIR instruments, you can specify the resolution. So typically it can be high resolution, -8, 16 per wave numbers, 32, 64. We've found that typically for pharmaceuticals, when you almost work like with a pure chemical, a low resolution like 8 works really well. For food, we found that 32 is typically okay. If you can't do 32, then 16, but we found for food applications that the resolution of 32 is usually okay. Okay, then you identify samples, constituents, and moving data from dedicated generic software to dedicated software is then obviously something that you need to handle. But I just wanted to mention the 2 things that you have to keep in mind. Selecting the number of scans, which should not be too low, otherwise you'll get noisy spectra, and resolution. Also, the higher resolution takes slightly longer than lower resolution. Software here, just the operation, again, just the dedicated software where you really would check your instrument diagnostics every day, check instrument diagnostics. And that's typical when you work with dedicated software with some of these instruments, there won't even be a keyboard or computer. It just happens within the instrument. You record the spectra, it can be stored in that device, you can collect it from that device again, and sometimes the instrument will even print you a little paper receipt after each analysis. So it's really set up in a really efficient way, speaking to consumers. Okay, I'm not going to go through all of this in detail. It just adds, again, sometimes allow you, if you scan samples and allow you to view the spectra, it's always worthwhile just to look at that and check that all the time. And the compatibility between software nowadays are quite good. And just important to remember that some of the standalone instruments do not allow viewing of the spectra, but the spectra are stored. So it might be useful to just download those spectra every now and then and just check that it still looks okay. I just want to point this out. So when you will get familiar with this for your own commodities. So if you work with wheat samples, so typically for ground samples, your absorbance values or your log over R will be from about 0.01, you can see this one, it's just above 1. So it would be from about 0.01 to 0.64. So this is 0.64, 0.67. So this would be a typical absorbance range for spectra. For whole grain, it's a bit higher. It would be 0.2 to 1.2. And this is, as you work with a commodity, you get used to what is valid for your commodity. And if those absorbance ranges suddenly change, then you know something is not right here, something that you need to pay attention to. And with this spectra, again, we know now, it's just 2 examples I've taken out. The top spectrum is a hard sample, the bottom spectrum is a soft sample. So again, this clear vertical bias between hard and soft samples. And you see for the ground sample, that distinction between hard and soft is not as large. So it's actually more towards the beginning than towards the end. So it's somewhat multiplicative. So actually from the other way around. So you do important then just to get familiar with the absorbance ranges to expect within your own samples. Okay, sample IDs is sometimes useful just to add numerals in front, 0, 0, 1, because if you want to sort samples, it's just so much easier. And not just 1, 2, 3, always add zeros. If you're going to have 1,000 samples, then do 0, 0, 0, 1. So if you want to sort samples to add reference methods, it might just be make life a lot easier. Okay, NIR contains multivariate information that makes it slightly more complicated. We have many wavelengths, up to 1,000 plus data points. And there are 2 important rules in our analysis. So there should be a known absorbency for the property, and that absorbance variance should be of such a magnitude that it's higher than the noise. So if we want to measure protein, we should know that protein or NH will absorb in the spectra, and that absorbance variance between the different samples must be bigger than the noise of the spectrum. And that is most of the case what we get. So this is just important. If this is not the case, you will struggle to do a calibration. Okay, so chemometrics specifically involves the mathematical treatment of the chemical or the spectroscopy data to extract information. So this is our magical tool to help us to get the information that we did not extract in a chemical way from our data. So the aim is then really to get the best fitting equation for the sample in the calibration. So I'll have about 10 minutes. I'll see how much I can fit in 10 minutes. So when you apply multivariate data analysis to an NIR data set, the first thing we try to do is reduce variables. So what we have with NIR, as they explain it, we have short fat matrices. So we typically have less numbers than wavelengths. So N is the number of objects, so samples. So the samples is down here, the variables down that way. So I should have actually, the variables would be say 1,501, and down here we might have 50. So we have short fat matrices. So the first thing we want to do is we want to reduce these number of variables to make interpretation easier. We want to improve projections, then we want to remove noise, find outliers, and then if we're looking for classes, we hope to see classes. So principal component is one of the techniques that we use to reduce the dimensions of the spectral data. So it decomposes the spectral data, but still describe most of the variation in the data set. So we reduce the data to a few factors, but those few factors still contains majority of the variation in the data set. So we do not lose information. So what the PCA is doing is eliminates the redundancy of the X variables by constructing a new matrix with columns that are linear combinations of the original column. So it's a data compression technique, and it's contained, the information that's contained in all the observed variables is then concentrated in a few what we sometimes refer to as latent variables. So it's referred to as principal component factors or latent variables, or when you apply PLS factors or regression factors or components. So there's different terms used for that. So when you have a data set, so I is objects, K is number of wavelengths, you can compress this data set into a number of principal component scores, and for each of scores there will be a loading, and the loadings we use to interpret the clusters that we might see within the score values. So typically this is what you would see. It helps you once you've applied principal component, you might see clusters, and with biological samples, it's seldom that we see a perfect cluster. We often see overlap, and then the loadings, although it's not spectra, it looks like a spectra, but it's not spectra, it's actually loadings at certain wavelengths. And this tells you if you see a difference, if you see structures, you can interpret these loadings to help you understand what is causing that difference. So the negative score here, the negative loading here correspond to the positive loading correspond to the positive scores, and whatever absorbs here, say is probably starch or sugars, will relate to the cluster that you see at the top. So PC scores is really helpful to visualize groupings, and the PC loadings help you to understand the groupings in those score plots. So the PC scores shows you the variation within the samples, and the loadings helps you to interpret the variation within the wavelengths, and which wavelengths really contribute to those specific classes. Principal components are orthogonal, and what we find is that the first principal component normally explains the majority of the data set, of the variance, followed by the second, third, and fourth. But we've seen, especially with imaging, even sometimes the loadings that contributes a small proportion still contribute useful information. I'm just going to do a quick example and try and explain how principal component analysis works. So if we take an example, only 2 wavelengths, 6 samples. So what we want to find is the most informative direction in space. So we want to describe that direction and make projections so that we can determine the scores. And that's after the application of mean centering. So if we have 6 samples, 2 wavelengths. If you have 2 wavelengths, then each sample will have a value for wavelength 1 and a value for wavelength 2, and you can plot it as a single number. So we have 2 numbers for each, so we could plot each of those as a single number. If we mean center, we will just move our axis to the center of the data. But what we could do now is we can add a 3rd wavelength. So now we increase the observations, and with increasing observations and variables now, okay, I didn't increase the observations, I've only increased the variables. Now we have 3 wavelengths. So each of these observations will have 3 values that's plotted in space as a single point. And we can continue like this. We can add a 4th, a 5th, a 6th, and then for those 6 wavelengths, each of these observations will eventually have, from those 6 in that dimension, have a single, will be plotted as a single point. But I'm not going to add more because then it becomes confusing. So now we want to calculate principal component analysis. So calculating the first principal component within the space of points, we need to find the direction of least squares. So we want to find the direction of maximum variation. And to do that is we can basically take this line and wiggle it in that space of points until we get the line of most variation. And that is determined by least squares. So we can make projections on each of these, and we move the line. We can wiggle that line until the squares of these values, the projections are the least value. And that would give us PC1. But then also when you project these samples onto your PC1, that will give you your score value. So now you've calculated the score value for each of these samples, and you can plot it on a PC plot. So now you have PC1, the score values for PC1. Now to calculate PC2, we have to draw a line also going through the center, diagonal to PC1. My line is maybe, we need to look at it from a different angle. It doesn't look now perfectly diagonal, but just imagine it's diagonal. So it's diagonal. We now, PC2 was positioned to find the second most variation in the sample set. We can again do projections onto that line. I didn't do it for all, and that would give you your PC2 score values. And similarly, you can do it for PC3. We now go in the direction of the third most variance. And again, if you draw PC3 a little longer, you can make projections onto PC3 and you can get your score values. So now you have score values for PC1, PC2, PC3, and you can plot it in a principal component plot. Somebody once explained principal components to me as you should see it as a rugby ball. Rugby is really big in South Africa. So if you take a rugby ball and you flatten it to some extent, so, and you have a swarm of data, to find your PC1 would be the long and, well, the longest direction of the rugby ball. So that would be PC1. Across the width would be the second, and then the thickness of the rugby ball would be PC3. Again, obviously you can now continue in different directions, adding more PCs. So this just quickly how I see, find it easy to understand principal components. And then the loading is slightly more difficult. That defines the orientation of the computed PC plane, which makes it slightly more difficult. So you can now, for a unit vector, determine loading 1 and loading 2 with respect to your original X variables. And so for every sample, you will get loadings at each wavelength, and that you can then plot. And those loadings you can then interpret, and that will help you explain and help you to understand your principal component plot. So maybe just now briefly, so if you have your data set, your applied principal component, so for every sample, you will get a principal component score for principal component 1, 2, 3, 4, as we've just illustrated. And for every wavelength, for each principal component, you will get for each principal component, you will get a wavelength, a number in the wavelength direction, which are your loadings, which you can then plot as a line. So it's not a spectrum, it's actually a loading plot line, which will give you the indication of the contribution of each wavelength in your principal component plot and help you to explain that. Where am I now? There we go. Okay, yeah, so the aim of our now getting to calibrations, so we have multivariate data, objects, a sample, we have our variables, and now the aim is to find a regression between, to find a linear or in some cases non-linear relationship between your X data and your Y data. And the linear modeling is to approximate the relationship in the data. And once that's done, it's tested and predicted in future. I just want to see where I am, whether we, because I see I'm running out of time. Sorry, if I can just check how many slides I still have. Oh goodness, I have a few more. Oh, but I can maybe, I think I should rather stop. I can, Rosario, I'm now just sort of before I would have elaborated on calibrations, but I think I can continue with this tomorrow. So I don't think I should continue with this, otherwise I will just do it in a rush. Is that okay? So if I've run a little bit out of time, but I'll try and run through this tomorrow quickly if necessary. If I will also watch Prof. Rosario's presentation. If she covers most of this, then we don't need to cover it tomorrow, or I might just give a quick overview if necessary. So thank you all for being here this morning and for joining us. And thank you, Zikrula, for handling this. If there's no questions, no hands, I think we'll stop now. It will be an hour. No, how long? 11? No, it's my hour and a half over. Yes, my hour and a half is over. When will you start, Rosario? At 2 or 1:30?
1 hour and a half, I think.
So you will start at 2. You will start at 2.
2, yes.
Okay, so Prof. Rosario will start at 2, and she will then continue with chemometrics. And tomorrow I'll see if it's necessary, I will cover part of this. Otherwise, we'll start with instruments and reference methods. Okay, if there's no questions, comments from anybody, those who at METU, that you can just come and tell me if you need anything else to be explained further. Thank you very much for all of you being here and being present. Thank you, Rosario, for being present as well. So I'll see you at 2. Okay, thank you all. Okay, and yeah, we'll just continue with the same link. We'll continue with the same Zoom link this afternoon. Okay, thank you all. We'll see you later. Thank you, Rosario. Bye.
See you later.
See you later. Thank you.
Thank you.
I think we can. Thank you very much.
maybe wait just 1 minute, please, for other persons, and we will start immediately. Please, could you confirm if you can see my screen, please?
I can see your screen, Rosario. I can see your slide.
Thank you very much. So, welcome to this afternoon session. We will talk about now chemometrics. We have a very good lecture in the morning about the chemometric introduction and an excellent presentation of Professor Marena with the statistical parameters that are evaluated commonly in the near-infrared spectroscopy techniques. So, my name is Rosario Castillo Felices. I'm professor in the University of Concepción in Chile. And now I will show you some techniques for pre-processing near-infrared data and the preparation of models of calibration and validation methods. So if you have some questions, I don't know the experience that you have with use of chemometric techniques, but please feel free just to ask by chat or open your phones, okay? So we will start now. Sorry. Okay. Professor Marena told us about some software and tools. I show you now some other softwares too, part of a Scrambler, PLS Toolbox, some MATLAB in general. You can use a lot of softwares, and I want to start with this description because the chemometric tools are included in most of the softwares, but depends on the objective that you want to perform. If you want to make classification, if you want to make a regression or application for quantitative analysis using chemometric tools, most of the softwares will give you enough tools to develop the models. However, if you want to use this software in order to calculate some other parameters, especially the analytical figures of merit, or like sensibility, selectivity, detection limit, or so on, maybe you need to do it manually, or you need to use another kind of software. In this case, I present this software, this free software developed by one professor of the University of Rosario in Argentina, called MBC1 and MBC2, especially for the session of tomorrow, okay? But this software and the others are very adequate for the tools that I will describe today and tomorrow. So, regarding the sequential multivariate analysis, today we know the basis of the near-infrared spectroscopy. We know that how acquire some experiments, the objective of the work depends if you want to make a quantification or classification or signal separation. You need to define a problem before the data analysis. You know that near-infrared spectroscopy is complemented mandatory practically with chemometric tools. So the first step to decide which chemometric tool I need to apply is to define the problem. What is the problem that I need to solve with use of near-infrared spectroscopy, okay? And when you have the answer to this question, you will see some or diverse methods to choose the best in function of the results and in function of the objective that you want to perform here in this multivariate analysis, okay? So after the definition of problem, you need to array your data. Marena show you and show us the array in a matrix X. The matrix X will be the principal input for all the multivariate analysis, okay? And it's very important that you visualize your data before the chemometrics tool applications. It's very important because maybe, as Marena said in the morning, maybe you have some outliers, maybe you have some problems in the spectral acquisition, and this part is very, very decisive to have very good results after the application of chemometrics. So this part is addressed in this step called data pretreatment. In the data pretreatment was the main goal of this session, in this first part in the afternoon, because this is the crucial stage, signal processing, before the application of chemometric methods. Maybe it's also a chemometric method, the data pretreatment, but it's strictly destined to remove irrelevant information of your data. And then you can decide what to do, quantification, classification, signal separation. But first, you need to clean your data, your spectral data, because data is not perfect, okay? And then we will talk about exploratory analysis, especially principal component analysis. Marena told us also the basis of PCA, the exploratory analysis most commonly used before the application of other kinds of chemometric methods like classification methods or calibration if you want to perform a quantitative analysis. So at the end part of this session today, today, we will talk about validation of the models since a point of view of the population and also statistical parameters regarding validation models. And then the models are ready to be used for future predictions, using also the evaluation methods that Marena showed us in the morning, like a lot of statistical parameters regarding error of prediction, error of cross-validation, and so on. We will pass these methods again, okay? So this is the input of our analysis for application of chemometric methods. The X matrix. The X matrix in this case in NIR data contains in each row the spectra of one sample. So rows are concerned to the samples, but columns are concerned to the variables. In this case, wavelengths or wave numbers, okay? NIR data is a sequential data. So we will use some algorithms, mathematical algorithms, especially designed for this kind of data, sequential data. And maybe these are a little different to the other algorithms just for discrete data, okay? So this is the input, the main input, okay? But the question is why data pretreatment is needed, okay? Because variation of chemical and physical properties of samples, as well as the measurement process and changes at the spectrometer will have an influence on the spectrum. I mean, three factors here are considered: the chemical information of the samples, the physical properties of the samples, for example, the particle size, the density, some other parameters that are very influenced on the spectrum, and the measurement process too, okay? The way that you acquire your data, if you are using transmittance, reflectance, transplectance, and so on, okay? So you have various parameters could affect the quality of the spectra. The task in this stage, the pretreatment stage, is to distinguish the true signal and the noise signal, and remove the noise signal and the irrelevant process to have only the very, very relevant data to perform a prediction model for quantitative or qualitative analysis, okay? So we have frequent source of spectral variation, like scattering. Marena told us about light scattering. Maybe in solid samples is the main problem. The light scattering produces distortion of the spectra, but in the X or signal response, not in the wavelengths necessarily, but it's very obvious in the signal absorbance or reflectance. So we see now some examples too, okay? The interaction of compounds, for example, the intermolecular hydrogen bonds could affect hydrogen bonds, for example, the wavelengths in a small amount, but it will affect this x-axis, okay? The overlapping absorption bands also affect the spectra and the quality spectra, but in some cases overlapped is a part of the chemical information. So we need to resolve the spectra, but we don't need to delete some overlapped bands. That's not the solution, okay? So pure reproducibility in the measurement process too, for example, by change in the path length, spectral distortions caused by spectrometry hardware, baseline drift, wavelength shifts, non-linearity response. We, in this course, in this lecture, we talk about the linear chemometric models because we think that NIR spectra has a linear response regarding concentration. Okay, so another kinds of methods are applied for methods, spectroscopic methods with a nonlinear average, okay? Another kind is a spectra of samples that are measured using diffuse reflectance. Diffuse reflectance, this is a very practical way to acquire spectra, especially in solid samples, but often are affected by non-homogeneous distribution of the particles. The size of the particles maybe is the principal main of light scattering in the spectrum, okay? So this different particle size affect this in this way, in this direction, the spectrum and the quality of the spectra, and is the major source of variation of the spectrum, okay? These particle size problems, the light scattering, have an additive and a multiplicative nature and vary from sample to sample. You can see, for example, one publication with analysis of a spectra of different particle size, and you can see that the spectra are similar in this direction, but in this direction are considerably affected. So you can see here the effect of that particle size. So we need to avoid this influence and the analysis when I want to make a calibration or classification model with predictive abilities and remove this effect. Except in the case that you want to measure precisely that particle size or so on. For example, in pharmaceutical application, maybe you can use NIR spectroscopy precisely to quantify the particle size of the drugs. Okay, you can do it too, but you don't need, in this case, remove this information because this information is very important for this model, okay? So it depends on the objective. So pre-processing is performed to remove the no-chemical biases from the spectral information or the real spectral information and prepare the data for future analysis. And some authors differentiate the word pre-processing from pre-treatment. That is, for some authors, is different because the correct word for the methods applied to the spectra, to the rows of the X matrix, are called transformation. But the methods specifically used or applied on columns or wavelengths are called pre-processing. But it's normal that you can find in the books and the publication papers the name for pre-treatment or pre-processing for all that you prefer before the application of chemometric tools for classification, for resolution, or quantification, okay? But we need to have in mind that the signal is a sum of the true signal plus the random noise. And we need to remove this random noise and divide this true signal in the relevant information plus the irrelevant information. But the separation of the relevant information and the irrelevant information could be addressed by chemometrics tool as well, but the random noise could be deleted or eliminated by smoothing techniques before, okay? This part requires more job in the computer, but random noise is mandatory to be removed before, okay? The smoothing techniques, and to separate the relevant information, we will need baseline correction techniques plus the application of some other methods for classification or calibration, avoiding the irrelevant information. In other words, we need a PCA, for example, and in the PCA, we will choose a number of principal components, and the rest will be in the residuals. And these residuals is considered the irrelevant information, okay? But don't worry if you don't know at this point what that means, a principal component, because we will see in the next slides, okay? So what techniques we have to perform? Smoothing, derivatives, baseline correction, multiplicative scattering correction, standard normal variate, normalization, well-common transformation, centering and autoscaling. This is a pre-processing techniques, and all the rest are transformation techniques, wavelength transformation, subtract some spectra, divide some spectra, transform each spectra in order to have a population with normal distribution, for example. There are many pretreatment methods. It depends of your spectra and depends of the problems that you have when you acquire your spectra, your data, depends on your data, depends of physical characteristics of your sample and so on. There are a lot of methods you can choose, but there are many important methods to remove information, irrelevant or noise that we will address now, okay? What? It's maybe not so common in NIRS spectroscopy, but sometimes we can see the noise, the random noise. And if we have the random noise, the best method to avoid this problem is to use smoothing, okay? And the smoothing has as goal the removing of the random noise by use of some algorithms easy to make using just a window, like this example. You have here a window. I put here a very big window, but the windows are usually smaller, okay? And you have different ways to apply the smoothing, moving this window, okay? For example, here, I don't know, I put an example. I have a window with 15 points, and you can measure the, or take the mean, the average of this point, and you will have just 1 point, and also another point here, and another point here, and then you will join all the new data, but you will lose variables. So you don't need to lose variables if you move this window just 1 by 1 or 2 by 2 points or 5 by 5 points, like in this graph, in this plot, okay? This is the moving average, and this is just a window with that average. And then you can join the new average, and you will have a smoothed spectra, avoiding the random noise, okay? I don't know if it's very common. Tomorrow we can discuss that with Marena. In our experience, if you have a good resolution, like 8 or 16 maybe centimeters at a -1, it's okay, and you don't need to apply smoothing in this case, okay? But the main problem is the light scattering by the difference of particle size. And in this case, you can use the multiplicative scattering correction. Maybe is the most used technique to remove the effect produced by the multiplicative and additive effects caused by scattering in NIR measurements, okay? This is an example of how are the spectra when they have scattering of light. One spectrum is similar to the others in this way, but
we've lost you, Rosario. I don't know if you can hear me.
Marina, I think the problem is with Rosario, because I can also hear you, but not her.
oh, sorry, I lost my...
Yeah, sorry, Rosario, we just lost you for a second.
Okay, again. Can you see my screen?
Yes, yes, we can see again.
Okay. Yeah. Yes. Okay. I was talking about the Lambert-Beer law, and considering the same sample, the same concentration, but you have different absorbance. This is a problem with scattering in the NIR spectra. So it's not correct. You need to apply something to correct this difference, and the effect produced by the application on MSC is that, okay? This is a spectra transformed by MSC. How we can apply this correction? We need a reference spectrum. Okay, this is a problem maybe of multiplicative scattering correction, because we need to choose in all our X data, X metrics, one reference spectrum to consider, and then we will plot our spectra regarding or respect to this reference spectrum. Okay, this is a regression spectra versus spectra. And we will have a linear equation of this regression spectra regarding two spectra of reference, spectrum of reference, and we will calculate an equation, okay? And this equation, or this regression equation, will have a slope and an intercept. And we will use these values of the equation to calculate the corrected new X spectra, okay? The corrected spectrum of one sample. One sample, each sample is submitted to this equation in order to have a new corrected spectrum. Just we need the intercept and the slope of this equation produced by a reference spectrum. But which spectrum is better to be used as reference spectrum? This is a question. And normally we use the mean spectrum. It's complicated because sometimes the choice is not the better, the mean is not the better, and you need maybe apply another method in order to correct the multiplicative and additive effects, but without a reference spectrum. And in this case, you can use another technique, in this case, call it the standard normal variate. The standard normal variate has the same effect as a multiplicative scattering correction, but in an easier way. What is the calculus for this correction? You have here the equation. You just need the original spectrum, and then you will calculate or estimate the mean of the spectrum values for every wavelength. You have a lot of data for each spectra, different wavelengths, and you will have the mean of these values and also the standard deviation of these values, okay? You will use the mean and the standard deviation. You will rest the mean and divide the difference by the standard deviation of each spectrum, and you will have a corrected spectrum without the requirement of a reference spectrum. So standard normal variate is applied to correct the same problem that multiplicative scattering correction, okay? But in an easy way. The results are very, very, very similar. Okay. And another pre-treatment method is the normalization. What is the objective of normalization? Normally, normalization is used to remove systematic variation produced by amount of samples. Different to say that the concentration of samples in NIRS spectroscopy and also mid-infrared spectroscopy is used to correct the amount of sample which is interacting with the light. For example, if you are using transmittance, if you remember some methods for transmittance, you have a path length where the light throw across your sample, and maybe the light is not, or maybe the pathway is not the same for all the samples, okay? But also if you have solid samples and these samples are incided by a light, for example, a Prof, okay? A light from a source, and all the samples will have the same interaction in terms of amount of samples. So in this case, you need to apply a normalization. And you can decide what will be the norm. The norm is a reference spectrum that you need to calculate normally using the sum of squares. Okay, this is the sum of squares Euclidean norm normally. You can use, for example, the wavelength with maximal signal as norm, okay? But you can also use another norm, for example, like the sum of each value of the spectrum. And you can use also the root of the sum of the squares of each value of the spectrum. And this is the Euclidean norm, very, very used in case of NIRS spectroscopy, okay? So we have here another expression called Kubelka-Munk. Marena maybe say more about Kubelka-Munk than me. I use this Kubelka-Munk transformation in case of reflectance spectra, especially diffuse reflectance infrared spectra, because as the transmittance, there are no linear relationship between transmittance and concentration. But you can find a linear relationship between, for example, absorbance and concentration. So you need to transfer transmittance to absorbance in order to have a linear response, signal response between spectra, signal, and concentration, okay? In the same case is in the case of reflectance spectrum, or especially diffuse reflectance, where we don't have a linear response of this reflectance with concentration, especially for applications, for quantitative applications, okay? So the Kubelka-Munk, sorry, here's wrong. The Kubelka-Munk is calculated by a simplified equation. Show it here. The equation is a little more long and includes another parameters. But here's the simplified first term of the equation, and you can transfer your reflectance values to Kubelka-Munk in order to have an answer or response related in a linear way with the concentration, okay? For drift, it's very recommended to Kubelka-Munk units and not to perform the chemometric tools just using reflectance units, okay? And some other kinds of pretreatment are the derivatives. Derivatives are used in order to reduce baseline effects and remove the constant background signals to enhance the visual resolution. If we have a linear equation, for example, if you apply the derivatives, the first derivative, you will remove the constant and you will have just a slope. And this is the work that derivatives make on your data, okay? So it's used in order to remove some deviation of the baseline, mainly, okay? So small difference, it's normal that small difference between near spectra are not obvious to observe, and some peaks are overlapped, okay? But if you separe the overlapped peaks, some small difference will be enhanced and you will reduce the baseline shift, okay? So if you are using derivatives, you will solve the problems of the baseline deviation, but you will solve also the problems produced indirectly by light scattering, okay? Because we will correct this dispersion of light in the direction of the response too. So if you use derivatives, maybe it's not necessary, maybe, to apply a part MSC or SMB, for example, okay? The first derivative is used especially for the baseline deviations, and the second derivative or first derivative and another derivative is a valuable tool to identify weak peaks that are not visible in the original spectrum. It means that the second derivative is useful, very, very useful and effective method to solve the overlapping of bands, okay? If you want to perform something to avoid the overlapping signal and to see for qualitative description of your spectra or for develop models for classification or regression, you can apply the second derivative. But the derivatives has a very big problem. Derivatives produce noise, okay? Derivatives decrease the ratio between the signal and noise. So you have to decide if the use of derivatives compensates or not the noise introduced by the mathematical algorithms. But we have a solution, it's the smoothing. Okay, if the use of derivatives produce noise, you can apply another method which includes smoothing before differentiation. And the most famous method is called Savitzky-Golay algorithm, okay? This method, moving window, obtain an average value of each window, but they apply also a smoothing of the spectra and differentiate smoothed data before, okay? We can see here some examples because we have another problem with the derivatives. The derivatives change the shape of the spectra and the interpretation of the spectra changes a lot. And maybe for someone like me, it's a little difficult to see some results when you use, for example, the first derivative. Because if you have, as in this figure, the raw spectra, and if you apply the first derivative, you will see the slope change, okay? And this is the slope change now, this is the pending, in this maximal will be transported to the 0 point here in the derivative spectrum, okay? So this point corresponds to the original maximal response of the peak. It's difficult to identify then where is that very important signals if I change the shape of my spectrum. So this is a problem. In the case of the second derivative, the shape also change, but the interpretation is easier because you have now as valley the maximal peak, okay? So you need now to see the valleys and not the highest absorbance peaks, okay? This is the problem when you use the derivatives. So the higher the degree of differentiation used, the higher will be the decreasing of the signal noise ratio. Please consider that. And the optimization of this process of pretreatment is do it by changing the number of the points. Maybe if you use points or window points very, very small, you will introduce more noise. So you don't need to use a window very small with a low number of points, okay? So maybe in NIR infrared data, we use 25 or 21 points window, and we don't have to noise, okay? Here we have some examples for the application of first derivative spectrum and the second derivative spectrum. This is the original spectrum with the scattering. You can see here the scattering of light. And if you apply the first derivative, the shape will change, the scattering is solved. You see in the zero, now the bands at the maxima here with zero sigma here. I mean, the interpretation is a little different. If you find after the application of chemometric tool, which variable is most important, you just need to approach these most important variable, bit variables, to the closer bands here in order to detect which bands correspond to the original spectrum, okay? This is just an approach. But in the case of the second derivative, you have here one example with the bands. This is a mid-infrared, but similar in near-infrared. You have here the bands at maximum in signaling absorbance in this case. But if you apply the second derivative, you will have the valleys, and you need to observe the valleys to interpret these bands and no more the maximum, okay? In order to have more information about the overlapped signal, it's normally used, commonly used the second derivative, and you will see here, sorry, I don't see that, okay? For example, just two bands, and if you apply the second derivative, you will see more than these two bands. Normally, you will see more than these bands, and if you have some shoulder, you will see now this shoulder like a separate band after the application of second derivative, okay? And also you correct the scattering and the baseline deviation, okay? So second derivative is perfect, but introduce noise, more noise, okay? Some spectral programs or chemometrics softwares has as by default the use of first derivative because it's practical for most of cases, first derivative, okay? Second is less used. Okay, and another kind of transformation is the use of logarithms. Logarithms is used in order to linearize the data or change to a logarithmic scale. Okay, the most known method is the transformation of transmittance and absorbance units to follow the Lambert-Beer law. Okay, it's very easy to do it, and you can apply the same as Marena said us in the morning with the minus logarithm of the reflectance to have the absorbance. This is another kind of transformation too, okay? So we want to practically deal with you, and I will ask you some strategies to solve some problems that you see in this picture, okay? Please look at this spectra and you can detect some problems in this kind of spectra, and principally maybe is the light scattering, the dispersion of the light here, the scattering is affecting the quality of the spectra for future analysis. But another visualization strategy is to see the relationship between the bands. And this is very important to introduce some other chemometric tools, no? Chemometric tools for pretreatment, I talking about PCA, pattern recognition, PLS, and other methods that needs the reduction of variables. Why? Because you can see here a higher relationship between the response in the different wavelengths. For example, we will see in this visualization step, we can see the high relationship, linear relationship between the absorbance of one wavelength, for example, 1000 regarding another wavelength, okay? This linearity is called in chemometrics collinearity. In this collinearity is a problem to analyze the data because the data are very, very related between variables, among all the variables. So we need to apply, when this happens, and this happens all the time in NIR data, we need to apply reduction methods, reduction of the dimensionality methods, like PCA, okay? So this is another problem that you can visualize your data, but you cannot see this problem if you see just this plot. Maybe you need to make or prefer another kind of visualization too, okay? But in this example, we see collinearity problem, dispersion or scattering. We don't see anomalous spectrum. Maybe one is a little bit different, but if you have on the layer, that difference is very notorious, okay? The adequate response, you can see here, the values are higher or not. The response is adequate or no. The Lambert Beer law is okay or not here in the data. And if you see your data, you can decide what or which strategy to use in order to remove the irrelevant information, okay? So now I have a question. I have an raw data, infrared data of samples of algae. Okay, by chat, I want to ask you if you consider some strategies in order just to remove the main problem of this spectrum, okay? So I want to ask you if you suggest some transformation, especially for this kind of data. And what is the problem? Which problem do you see in this example? For example, I will open this chart. First derivative, and you solve all, kill me. Baseline shift, yes. And the other problem is a baseline shift. We have a baseline shift, yes. It's decreasing, and decreasing again. Another problem, you can identify another problem. Scattering. We have scattering, and this is a big, big problem of the data, okay? So we will apply first derivative, okay? But if I just want to apply one method without to change the shape of my spectrum, I don't want to change the shape because I need to make an interpretation, qualitative interpretation, I don't know. But which method could you use without change the shape of the data on the spectrum? For example, yes, that's good. Very good, Marena. You are experimenting with MSCA, you know. And also standard normal variate, for example, because in MSC, we need a reference spectrum. Really? Okay. If we apply this kind of methods in order to correct the scattering, we will have this spectrum. Using in this case as reference spectrum, the first, the mean of the data, okay? And this is the response using the standard normal variance. It's practically similar here. You can see that, okay? Let me see that. Using a fiber optic in the reflectance mode, do we call it numerous spectral and average before any future treatment? Of the same sample, replicates? Are you talking about replicates?
Sorry, of the same sample, put as a layer, for example, in a dish, and try with the probe to collect spectrum from different points. So I see that there is a shifting in the y-axis, although in a powder form.
Okay, yes, you can do it. You can do it, but you can do it just with some depends, it depends. But you don't need to expect the y-axis will be the same for all your replicates. Don't lose your time expecting that, because you can apply this kind of methods into solve in one step all this problem, okay? Don't expect that. Now you know that we have some sources of variation that's normal, especially for solid samples, okay? But maybe when you use Prof, I don't know, I'm not sure, but maybe you have more noise. This is normal too. In the Prof instruments, in our experience, the noise spectrum is common with we using just Prof and not a laboratory and table instrument. There are differences in the quality of the spectrum. Maybe you need to apply smoothing methods, okay? Replicates, yes, it's better to have an estimation. Tomorrow we will talk about that in order to know the signal uncertainty, okay? But not, it's a mandatory to have a lot of values to have just a mean, maybe with 5, depends on your data, it's a variation, but maybe 2, sometimes 2 spectra, I don't know, okay? So how do you treat your data with derivatives? The question is, what's the correct number to apply the first or the second derivative? Here I have an example of this spectra with application of a window with 15 points in a second derivative. And you can see here the effect produced by the second derivative. And we have now very definite peaks, no overlapping, but we have another problem. What is the problem now? This is the spectrum. This is the spectrum now. Okay, I separate the overlapping peaks here, but I added a lot of noise to my data. So this have solution or no, depends, just changing the number of points here, okay? If you change this number of points, you can improve a little your data with a good separation here, but less noise here, okay? But please be careful, because at this point, this noise is a little dangerous too, okay? So you need to estimate the adequate number of points to apply the derivative, especially in case of second derivatives. The first derivative, the noise is less, but exists, okay? So I will back here. I don't know if you have questions about pretreatment techniques.
Rosario, can I just ask quickly, those points that you've now increased from 15 to 25, those are the smoothing points that you use together with the derivative. Is that correct? It's not the derivative gap. It's a number of smoothing points.
The number of smoothing points. Yes, that's right.
Okay. Yes, okay.
Yeah. This example was performed by Savitsky-Golay method.
Yeah.
So we decide the number of the smoothing points. Okay.
Thank you.
Yes. And there are many other pretreatment methods. That's what we are showing now by time result, the main transformation, okay? And so we have another kind of pre-processing method. Mean centering maybe is the most used for spectral data. Mean centering means to, here I will go to the X matrix, to estimate the mean of each column. And then we will rest the mean of each value. This is the mean centering. And then we will have the X matrix mean centered for a best visualization of data for application of, for example, of PCA. Okay, is to have now in place of the mean, the 0 value. Okay, the 0 will have the reference axis now and not the mean of the data. Okay, this is the mean centering, is applied on columns and not on rows. How important is the order in which, oh, this is very, very important. I think so, because first, okay, talking about mean centering, for example, mean centering will calculate here average or mean of each column. But if you have noise, this step will be wrong, okay? If you have scattering and then you apply the mean centering, you will have some effects, not desired effects. So you need to apply first transformation, rows, and then mean centering, okay? Or pre-processing techniques. First transform. And then, for example, in the transformation, you can also must to follow a logical pretreatment steps. For example, if you applied first derivative with a correct number of points in smoothing, and you have a very nice, you don't need to apply again another pretreatment like MSC, because the first derivative removes the problem produced by scattering in an indirect way, but they correct that, okay? This is unnecessary. So if you have, for example, normalization, maybe normalization by the amount on the sample interacting with the light, okay? You can apply normalization of your step, and then, for example, you can apply an MSC or to avoid or first derivative, because the main are absolutely different. The amount regarding the light scattering, for example. Okay, so you can say, maybe you can first correct the light scattering in their normalization. There's not a problem. You can test and see the errors and see the effect produced by the order when you are applying in a logical way the transformations. But there are combinations, there are very, it's too much. For example, normalization. Then scattering correction, SNB or MSC, and then derivative is too much. It's too much. And then smoothing, because the derivative will produce noise. So reproduce this result in order to predict a new sample concentration will be very difficult with a lot of pretreatments, okay? Please remember the parsimonious principle. At least you make on your data better for you, okay? Don't try to mixtures of pretreatments because they are not robust, okay? Please that. But the order is very, very important. Okay, so let me see here. We can continue with PCA. I repeat this slide because we finished this part. This is the crucial stage. Look at, and the optimization of the chemometric tools consists precisely into apply different pretreatment strategies and then exploratory analysis, then classification, calibration methods. And if you have results with higher errors, of if you want to reduce these errors, to back again to this point, to the data pretreatment, and apply again another strategy in order to obtain in this part, in this step, better results. If you have your results, okay, you're happy now, but normally we try another pretreatment data, okay? And apply it again, and you perform a table with your results, and then you decide what is better. What is better, which pretreatment was better for my data. But this pretreatment needs a chemical or physical interpretation, okay? No, please don't think in a random result after application pretreatment. It has, normally we have an response to our questions, an answer of our question when we see, for example, if first derivative has the best results. Oh, okay, my data has deviation of the baseline of scattering to, okay? We discover the problem sometimes with the result of the data pretreatment step, okay? So normally we continue with exploratory analysis like PCA before the application of the different kinds of chemometric techniques. Chemometric has different goals. For example, classification. For example, quantitative analysis. For example, just to resolve separate overlapped signals before to up classification. It's like a data pretreatment tool, okay? But you need to perform first an exploratory analysis in order to detect outliers or anomalous samples, and also to see some correlations between the samples, groupings, correlations or relation between the variables, to wavelengths, for example, or correlation between sample with wavelengths, okay? And you can see these results in the application of exploratory analysis. It's a best strategy to apply chemometrics in general. First, data pretreatment, then PCA, okay? And then you can decide what method to apply. Okay, exploratory analysis, the most famous exploratory analysis method is the principal component analysis. And Marena told us the principles of this method. This method has more than 100 years up to chemistry, but also to other sciences. So the concept is very well known, but I will repeat some equations and some information about the principal component analysis in order to take this basis and this concept also in the description of the other chemometric methods, okay? We will see and think in our data like a multidimensional space, okay? And this multidimensional space for the human mind is in a normal case, like me, just to reduce it for a 3 dimension, okay? More than 3 dimensions, it's very difficult to imagine. And the principal component analysis can be explained by the description of the data in this multidimensional analysis that we don't have the possibility to plot all the time. Because as Marena showed you, with that simple data with 6 samples or 2 variables, it was very, very intuitive for me to think in the possibility to apply the same concept, but now with a lot of variables, 100, 200, 1,000 variables, a lot of variables. It's exactly the same, okay? And can you imagine to plot variable 1 versus variable 2 and see the projection of your sample regarding this variable, and then change variable 1, variable 3, variable 2, variable 3, variable 3, variable 100, variable 200 versus variable 600, and so on. It is impossible to see all the combinations you have, okay? But if you have your data in this multidimensional space, you will have a distribution of your points in this multidimensional space with a shape. And this is my example. This is the shape of my example, a banana, okay? The banana has different axes describing the most part of this sample, like a vector, okay? you can see here the vector describing the maximal amount of information. It will be called variance in our cases, okay? This vector describes the maximal variance. This is a concept of the principal component. It's a new variable formed by the linear combination of the original variables that describes the maximal information of our data in the multidimensional space, okay? And the second PCE, or principal component, will be orthogonal with this first vector and describe the second most informative variance or information of our samples. In this case, this vector will be this one, okay? And the third component or principal component will be a vector describing the third maximal variance or information of our sample, which is orthogonal to the second and to the first principal component. And this is this vector, okay? It happens with our samples, with our data too. But then we need just to plot as axis the principal component, and then we will estimate the projection of our samples regarding these principal components. In mathematical terms, it's explained also by algebraic equations. This is our data X matrix. Each row is an spectrum, each column is a variable. This matrix will be decomposed by different algorithms used, normally use singular value decomposition or Nippel's algorithm. And the X matrix will be decomposed in two matrices. This first one is the score matrices and is related to the samples scores. And this is the loadings matrix, and the matrix of loadings are related to the variables, I mean to the wavelengths, okay? So if we plot this scores data, we will see the projection of our data in this space formed by new variables called principal components. If I do the same with these loadings, I will see which variable is most important for our data, okay? But the size of this matrix could be different. It could vary depending of the number of columns here that are the same number of the rows here, K. K is this number. And this is the number of principal components, okay? We can reduce, for example, 1,000 variables to 3, 4, 5 principal components. The problem here in the principal component analysis is to decide how many components I need. And there are methods to estimate how many components I need. But the principal method consists in to find the maximal variance explained per 19% of information of our data, okay? So we can decide how many K columns or rows I will use it in these matrices, scores and loads. For example, if I have 3 components, and with 3 components, I have more than 19% of information over data, we will have here 3 columns and 3 rows in the L matrix. 3 columns here in T matrix and 3 rows in the L matrix, okay? So we can plot now the first column versus the second column here of the T data, and we will have this kind of plots, the scatter plot, okay? Now we can change PC1 versus PC2, and I see the projection of my samples, the scores of my samples, and sorry, I will check here the groupings of the samples, okay? This is the possibility to see the distribution of our samples regarding the new axis called the principal component. But if we plot now the values of this matrix, loadings matrix, regarding this first row, second row, and third row, we will have the contribution of each original variable to this first component, second component, or third component, okay? And I will have the higher values, positive or negative, identified as the main contributors for the first component, to the second component, and to the third component. But if we have the same axis of coordinates, for example, PC1 versus PC2 for scores and loadings at the same time, we will see the difference between the distribution or groupings of samples, the relationship between samples, the relationship between variables, and the relationship between samples with variables. How? For example, here we have two kinds of data. This is a differentiation of root species by NIRS spectroscopy. And this is the same, but another kind, I mean, the same method, but using LG species, okay? I want to explain this second example because we see here just a two-dimensional plot of scores and easy to interpret that. Please look at this grouping of samples said as that the samples have something in common that are different from other group of samples, okay? Here we can see 3 groups, for example, or more, 1, 2, 3, and so samples between these 2 groups. And we can see also the loadings plot and identify which variable, original variable, is related to each group. For example, this sample in this part, upper and left, you can see here that this sample has higher absorption at these wavelengths, located at the same place of the projection of PC1 versus PC2. And this sample, for example, regarding to this axis, PC2 and PC1 are related with these wavelengths, for example. This sample has intensive absorption at these wavelengths. And this sample has intensive absorption at these wavelengths, okay? A relation between the samples and wavelengths. And you can also interpret these results finding some relationship between the wavelengths. For example, if you choose here 2 wavelengths, this wavelength and this wavelength, and please, in your mind, project this wavelength to the 0 point. This is the 0 point, okay? This is the 0 point. Project this a line until the 0 point, and then the 0 point return or back to other wavelength. For example, this wavelength, okay? And then estimate, please, the angle formed by these 2 imaginary lines. And the angle will be a good, and if this is the result, you will have a higher relationship between these variables. If you draw an imaginary line between 2 variables and the angle is around 90 degrees, there are no relationships between the variables. And if you have, for example, a line in opposite way, for example, this wavelength regarding this wavelength, and you can trace the line to the 0, and you have an angle next to 118 degrees, you can see, or you can interpret the result as inverse relationship between these 2 wavelengths. As this wavelength increase, this wavelength or this band decrease for the samples, okay? So this is the interpretation that we can make from the principal component analysis. Relationship between samples, samples with variables, and relationship between variables too. But the first thing, maybe the relationship between samples is very important because you can see groups. And for classification, you will see now that methods based on principal components will be successful. Then for classification, principal component analysis is not a classification method. Please take in mind this concept because you are just exploring your data. This is a spontaneous separation. You don't need to a class. I put the colors because I know, but if you don't know, that's no problem. You don't need more information to perform the analysis. You just need to do the X matrix, okay? This is not a classification, but you can see if you have groupings. This is exploratory. Classification is a term used in chemometrics for prediction of classes. I mean, you develop a model in this calibration step, like Marena told us, and then you validate your model, and then your model is ready to be used as a predictor. But before, if you don't have a validation, if you don't have a predictive tool, you don't have a classification model. Not yet, okay? This is just an exploratory analysis. And also, I want to talk about outliers. The outliers are the samples which are very different to the rest of the population. Maybe if you have one sample for that or that square, you will see some difference in the sample, and this sample could be considered as outliers, but some specific statistical techniques are used to detect it, okay? You don't need to remove necessarily. You need to apply a statistical method to decide if it's really an outlier, because you can find this sample like an outlier by one method, the statistical method, by other statistical methods, it doesn't, okay? So you need to decide in order to remove with at least 2 statistical methods to decide if this is outlier. If this is outlier, maybe because the spectrum was acquired in the wrong way, but maybe it's good. But chemically and physically, it's different to the rest of the population, okay? So maybe, if not necessary, that you remove the sample. Not for classification, maybe, but maybe for regression, you will have very good results if you remove this outlier. But we can discuss that later, okay? So regarding PCA, I don't know if you have questions.
Rosario, would you mind if I ask a quick question?
Okay.
I find the way that you do the loading plots quite interesting, because normally we use loading line plots, and to correlate the positive, negative loadings then with the PC plot is quite difficult. So this is a much easier way to interpret loading. So I just want to double check. So what you've done, did you plot the loadings of PC1 against the loadings of PC2? So that's what you did here. Is that right?
Yes, you have, Marina, you show in the morning another plot of loadings. That is very practical too, especially for interpretation of which variable is most important. Yes. This kind of plot, the scatter plot, is especially used if you want to find which variable is related at the same axis of coordinates with the samples.
Yes.
For this goal, it's suitable. But for interpretation, maybe another plot is easier to interpret.
Yeah,
for
so
me.
So there's a purpose using loading line plots for some interpretation, but I find this plot to interpret the scatter plot a really interesting and a much more easier way. So is this plot called something specific, or do you just do a scatter plot loading 1 against loading 2, or loading 1 against loading 2?
No, you don't need to change, because if you change, for example, here, PC1, PC2, and then we will see the plot PC1 versus PC3, scores and loading difference, no, the interpretation is wrong.
Yes.
You need the same axis.
Yes,
in both.
Okay.
And you can do it the same now, changing for both the pieces. 1 and 3,
yes. Yeah, this is really, and so on. Yes. Yeah, I found this quite interesting way of interpreting. Yes, thank you very much for this, Rosario.
Okay.
Thank you.
Okay, okay, more questions? PC A. you can imagine the interpretation, the data, when you are using the first derivative or the second derivative. It's a little bit complicated in the plot of the lines. But here in this scatter plot, it's less complicated, okay? But you can,
can I ask
have a chemometric course there. Then,
sorry, can I ask you one more question, Rosario? Just going back to that loading scatter plot. So how it actually shows the important wavelengths. When you plot this, does the software automatically highlight those wavelengths?
No, it's not automatically. In fact,
you look at the extremes and you find those wavelengths.
You can find manually plotting your data and then put the name of your variables. This example, for example, was made in MATLAB using the singular value decomposition algorithm. And then you can plot the data, put the names, and you manually identify your data. Yeah. For example, if you want to have some information, and thank you for your question because I forgot something. For example, here the main interpretation of these scores is that this group is absolutely different to the rest, okay? Because this is the first principal component, and this is the principal source of differentiation of our sample. And the second is the second differentiation most relevant in our data. So the first, in this case, I told you, I tell you, because I didn't, this is an algae species, and this is another species of algae, okay? And these algae are on the summer, and these algae are on the winter and spring sampling, okay? But the principal or the main difference is the species, because always, all the time, PC1 will describe the main differentiation source between the samples, okay? And and I have the differentiation identified, this is species. I need to identify now which variables are most relevant for this separation. And this separation is produced by the PC1, so I need to identify which original variables are contributing more and more measurements to the first principal component. So here, first principal component has the 0 line here, and you can find now which variables are or have high values for PC1. For example, this one. This one is 0.16 maybe, okay? This one, and also this one is minus 0.15, around. This is an approach, because they are so far to 0 regarding to this line, okay? So this variable, this variable, this variable, this variable are very important. But these variables here or here not, because they are very, very small loadings, so they are not important for the PC1. And the PC2 is different because the PC2 separate the samples by seasons, by seasons. For example, here one season and here another season. And I forgot now this line, and I will be concentrated just in this line. So I want to identify which variables, original variables, are responsible for the separation of sample by seasons, okay? So I find this sample, and also this sample, and also this sample. There are no problems if it's positive or negative, are important equal, okay? So this sample is important because it has a higher loading for PC2, 0.12, for example. And this one too, and this one too. But this one are related to these samples, and this one is related to this sample. Left to left, right to right, okay? This is the interpretation. But you can find which original variable is relevant for each PC if you see the values of the loadings for each PC. For example, this one is very important for PC2, but not for for PC1, but not for PC2, because it's smaller. But for PC1, yes, it's very important. So you can decide, okay? And the same if you are plotting another pair or air pieces, okay? So another question?
I just want to stress this, Rosario, the fact that you've explained this now is really good, because I find that often students, when they start working with NIR, they misinterpret PC1 and PC2, because PC2 is written on the y-axis. They take the zero line of PC1 as a zero line for PC2. So this is really important that you've just stressed. So when you separate PC1 along the x-axis, it's that vertical zero line, that's the zero line for PC1. And PC2 is the horizontal zero line, separates based on PC2. And I often find that students do that the other way around. So this was really, it's good that you've explained this. Yeah, thank you.
Okay. And if you have a lot of variables next or close to the 0 point, you can remove it because they are not important. And you can try it again, the PC, and maybe you have the separation. Maybe you will have a best separation, maybe not. It's not mandatory. But now you have here a region without contribution or high contribution to the separation. So in order to work with just, for example, filters, you can remove this range of the spectrum for future analysis and just to work with these bands, with these filters, for example. If you are working in a project when you want to apply the spectroscopy as alternative method, and you don't want to buy a lot of equipment for a process or light analysis, and you just need simple technologies, you can use filters, but you need to identify which filters do you need. Okay, so you can remove this and try again the method, and maybe you will have the same separation, or better even, or maybe not, because they have a little contribution, but they are important. So you can test, okay? This region of 0. Here we have the separation is good, okay? This is irrelevant, but maybe if I want to differentiate, for example, winter from spring samples, maybe this region is important. So I need to decide looking for the information using also another pieces, okay? And then when you discard the importance of these variables, you can remove the range and try it, okay? So it's already PCA. This is the exploratory analysis to detect outliers and to detect also, maybe tomorrow I will back to the outlier detection because we will have more information about how works the PCA analysis and other chemometric tools, okay? So for the second part and before the break, I just want to show this slide regarding the development of predictive models. Marena told us about this development in an excellent way because I think you know now that you first have to perform a modeling using a training set of samples, but then you need to validate your model, okay? And only if you have your model validated, you can use this model for future prediction of a null samples analysis, okay? But for the modeling or training step or calibration step, this is also the name. We use modeling with one L, with two L's, training, and also calibration. But calibration, you can think that calibration is related only to regression. And there are a lot of authors using this term also for classification, but they use this word to describe the modeling step, the creation of the model, okay? The discovering of the equation, the mathematical equation, in order to predict them the concentration or the class of one new sample, okay? For the modeling or training, we need a calibration set. What is the calibration set? The calibration set is a group of samples. There are a lot of samples which correspond to a population of samples which have characteristics that I want to include in my model. For example, if I want to include in my model samples coming from different seasons, like this example, I need to use a calibration model with sample of different seasons. But if I know that the place where I did the sampling could affect the chemical response of the samples, I will include this source of variation also in my calibration model. And if I know that other things will affect the spectra of my data, for example, on my samples, for example, the temperature, the day, the analysis, I will include all these variation sources in my population in order to have a very, very representative and robust calibration set of samples, okay? Mathematically, what I need to perform this step modeling or training, just the X matrix, but if I want a quantitative model, now I need a dependent variable Y, which is a class, column, or matrix even, or chemical properties or physicochemical properties and so on. Because now I will build a model, okay? The validation is the step to prove this model in terms of statistics. How is the error? It's low, it's higher. I need to perform another pretreatment in order to reduce the error. I need and I have a very good answer for just, for example, screening or analytical and for example, quantification of drugs. So I need to decide here if the statistical parameters of error are enough for my data or for my problem, okay? And Marena showed us a very, very long list of different parameters: RPD, standard error of calibration, standard error of prediction, explained variance, coefficient of determination, and so on. The validation step is to visualize this table and to decide if the errors are good or not, are suitable or adequate for future prediction of my samples, okay? And the third part of the chemometric application methods is a prediction, is to use the mathematical equation found in the modeling step in order to predict the concentration or the class of a new sample, okay? This is a prediction. What I require for validation, I also require an X matrix and a dependent variable, because I need to know in validation samples the concentration of the class of my validation set of data, okay? But when I talk about prediction, a prediction is an unknown sample. I don't know anything. I just have that this sample is similar to the population or my samples in the modeling, and I just need to require I just need the X matrix, the spectral matrix, and I will have as output the class or their concentration, okay? I don't need anything else that's the expected for prediction step, okay? So in validation step, maybe we will see more statistical and some description and some equations, and they are not difficult to estimate. But please take care with that because it's not difficult. Maybe the most difficult part is to understand the chemometric methods, but the application is very, very easy and simple, and most of software will give you the validation or statistical parameters are ready for interpretation, okay? Don't worry for that, okay? But before of this description of these statistics parameters. So we will have a break now. It's okay. Marena or Mesit? Yes,
yes, yeah. Thank you, Rosario. I think we'll have we can have a 30-minute break. So we'll start now. We have to get all the times right. It will be 4 o'clock in Turkey. It will be 3 o'clock in South Africa. In Chile, where are you now? 10, 11.
Yes. No. Now is 8:30.
Oh, it's only 8:30. Okay, so we'll meet at 9. So 9 o'clock in Chile, 9 o'clock in Chile, 4 o'clock here, 3 o'clock in South Africa. And I don't know any other countries who have joined. So we'll meet in, so we'll meet in half an hour. Thank you very much, Rosario, for this. This was really, really interesting and very informative, and I'm sure easily understood by everybody. Thank you so much. So we'll see you in half an hour. Thank you. Thanks, Rosario.
Bye-bye.
Bye for now.
Okay, we will continue.
Let's see. Yes, I think you can continue, Rosario.
This Marina.
Yes, yeah, I think it'll be
okay.
It will be okay if you continue. I can see there's some people there already.
Okay.
Thank you.
We were talking about the steps, the different steps to prepare the models for predictive main goals then, but now I want to talk about how we can split the data before the modeling, before the validation, okay? We need to think in our data as a total data, a set of samples, so near spectral data, and divide this data in two kinds of data. One data set, the first one for calibration or to prepare the model, and the second one for the validation set. Maybe it's not possible because maybe you don't have enough amount of samples to separate this data. It's difficult, but you need to have data in the most possible you can, because it's better if you validate your data set with samples that are not used in the calibration step, okay? It's better if you use an external validation data set. Different in terms of identification samples, different samples, but samples from the same characteristics of the calibration data set. I mean, your validation data set has also the characteristics of noise, of equipment, of time acquisition, analysis obtained in the calibration analysis tool, okay? And if we complete with this data set, a complete data set, and then we separate the calibration, the validation with similar characteristics, we will have a good result in the validation step, okay? And the model will be ready to be used as predictor for prediction of new samples, but these new samples needs to have also the same characteristics of this calibration and validation sample set, okay? How many samples we need for calibration, how many samples for validation? If you have, I think mathematically and statistically more than 20 samples, you can apply the very different chemometrics tools. But if you have less samples, it's difficult. It's difficult because you are using reduced techniques like PCA or PLES, reducing in dimension space techniques. But if you have more samples, you are not limited to the choice of the number of latent variables of principal components for analysis. So if you have more samples, it's better, okay? The number of samples, I know, it depends on your analysis, but if you have 14, 15, 100, it's better because you can have a good number for calibration data set and also for validation data set. A recommendation is maybe 2 of third part for calibration and 1 of third part of the data set for validation data set, okay? And then you can validate your calibration data set with another kind of validation, internal validation, using the same samples of the calibration data set. But it's better if you apply then external validation of your model, and you will see in terms of the real prediction ability if your model is suitable or not for future predictions, okay? But if we have now the samples, and if we have also the number, the suitable number of samples for each data set, calibration and validation, how characteristic should be the calibration data set in comparison with a validation data set. Please look at this slide. Here we have a distribution of the total data, calibration and validation samples, okay? in multivariate calibration, we use the term samples, even if we are talking about standards, because we don't have pure reagents like standards, but we also use samples because we have the analyst of interest, but we have also the interference present. So maybe it's not necessary use standard, pure standard, because the chemometrics has as a goal to improve the selectivity of techniques, I mean, to distinguish the signal corresponding to the components of interest, even in presence of interference, okay? So the characteristic chemical, physical-chemical characteristics of the calibration validation data set should be similar, okay? Should be similar, and this data could be split in different ways. And here we have some examples. For example, this is a splitting of data in calibration data set and validation in the case of the low number of samples which have similar conditions and similar properties in calibration and data set. This region, overlapped region, but the rest of the sample of calibration and validation are not equal or similar, but it's acceptable, okay? If we have this case, it's acceptable, but it's not the best distribution of our data, okay? But if we have this case, for example, calibration data set describing a lot of variation and validation data set comprising only one kind or two factors affecting the variation of data is not recommended, okay? Calibration has another interference, maybe another spectral noise, baseline deviation, and so on, but the validation data set, no. That's not recommended, and please join all again and separate or split your data according to a real homogeneous distribution in both sets, okay? Including all the variants. Calibration data set has a behavior like just one part of the validation data set. This is not recommended. Either you need to join all the data and split again for an homogeneous separation, validation, and calibration data set. Okay, what is this separation? This separation is a separation with calibration data set with the same characteristics, like that, okay? But if you have this separation absolutely different of calibration and validation data set, the model will not validate it. And if it's validated, it's just at random, and you will predict with a higher error. So please consider this fact. You need to have the same characteristics in both sets before that split. And then split the data, by assessing the distribution of the data sets with similar characteristics. And when you perform this splitting, please include all the possible factors of variation of samples. For example, measurements factors like the operator or the temperature conditions, the sampler, for example, the origin, the sampling, the varieties of your sample, the storage conditions, the particle size that you can find in real samples, the residual moisture after a drying process, for example, of your samples. And please consider all these factors with the values of plus or minus the error, okay, of each measurement. Please include all these factors of variations in the data set. And then you have your data divided, you will follow this scheme. For quantitative models are useful to predict some physicochemical, chemical properties, concentrations, for example, distribution, particle size is also is possible to quantify by quantitative regression models, and you need two kinds of data. The first one is your spectra, of course, your spectra, your near-infrared spectra, but you need also the value obtained in the analysis of all your samples, obtained by analysis of a method or reference method. For example, HPLC or wet chemical methods. You know what you can use in this analysis of reference. And then the spectra will be passed for a pretreatment stage, and you will apply different pretreatment strategies. Then you will build a regression, apply the regression method to build an equation of the calibration, okay? This step is very important because this equation will be used for prediction then. But in order to build the regression, to apply the regression method to obtain the equation, you need this value of the reference method, okay? So you have now the X matrix with the spectra and the Y-dependent variable with the values of reference. This reference will be also a matrix values. You just need to define the method. For example, PLS1 is a common method for a vector. Here, if you are using just a vector, but PLS2 is used for a matrix of responses, okay? But we will reduce this lecture for analysis of one vector in order to simplify the explanation, okay? And also you need to know the errors produced in this analysis of using the reference method. As Marena showed us earlier, you see in the table, for example, the standard error of the laboratory and some other parameters that you use to compare the error obtained by AIR compared with that reference method, okay? And then when you have this equation, you can validate your data using an internal or external data set. What is the objective, the goal here? The validation step evaluates the statistical parameters of the model to be used as a predictive tool. In the case of methods like PLS or PCR, and by reducing the number of variables to latent variables or principal component vectors, this stage, the validation step, provides us the number of latent variables suitable for prediction too. I mean that the choice of the number of components will be fixed in this step, in validation step, especially in one method called cross-validation, okay? One validation method called cross-validation. There are a lot, very possibilities, no methods to choose the validation, like cross-validation and validation using external data set, and I will show you some of them, okay? But please remind that the cross-validation, all the samples are used for modeling and also for validation in an alternative way if you don't have the possibility to use an external data set, okay? If you don't have an external data set, and maybe you have to, you need to perform a cross-validation, but actually, if you validate your data only by cross-validation, maybe it's not enough. And it's better and it's realistic, more realistic if you validate your data using external data sets, okay? And now we will describe how perform a cross-validation and external validation, okay? There are many methods to show the way how cross-validation is applied on your data. The most famous is the leave one out cross-validation. In this process, of this approach, each sample of the calibration set serves as evaluation set or as sample prediction set, okay? How it works? Let me show you here. This explanation is very good. You will have here the training set samples, and the validation set samples will be one of the training set samples, okay? The modeling set, one of these samples, you will choose the sample and exclude of the analysis and to build a new model using all the samples excepting this validation sample. Just one sample, okay? I mean, you leave one sample of the training, okay? And with this training set, you build the model, you obtain the equation, and then you use the equation to predict the concentration or the response of this sample, this validation sample. Okay, so now you have a concentration, a predicted concentration of this sample, and one model. Then you will back this sample to the modeling set, and you exclude another sample of that training set, another sample, and you repeat the algorithm of building another model, predictive model, with all the rest of samples of the training set, excepting this sample, and then you apply the equation to predict the concentration, for sample concentration, of this sample, okay? Now you have another predicted concentration and a second model. Then you back the sample, the excluded sample, and exclude another sample of the training set and repeat this process until every sample has been removed and you have different N models for prediction of this concentration of each sample. Then you can estimate the error of the excluded samples by comparison of the real value of concentration regarding the predicted value of each sample, okay? And you can estimate the error. Yeah, and also this, you can plot this error in function of the number of components. And if you find the less error, you can select this number of components. Okay, this number of components will be called, in most of cases, latent variables if you are working in regression, with regression methods, okay? But this is the concept of the leave one out cross validation, to use all the samples of the training set as validate samples, or validation samples. But you can also can leave more samples out of the models, okay? And this method is called leave more out cross validation. The validation approach is the same as the first case, but now you remove a group of samples from the calibration set in place to remove just one sample, okay? Then you build the model again with the remaining samples, predict the removed samples, and repeat the procedure until each group of samples has been removed and predicted once, okay? This is the same concept using just more samples. And then you have also other methods to perform if cross-validation is okay. Another kind of validation is the k-folds cross-validation. This is a very interesting method too. This validation approach uses a segment of calibration of sample as evaluation set. Here we have the plot, and you have a very high number of samples, for example, but you don't need to select just one sample or two samples. You need to select a segment of all your data, okay? And you exclude this segment and use the rest for training fault, a model with different segments, and build the model and obtain the equation. This equation will be used for the prediction of this group of samples, this validation fault. This is a segment of samples. And then you back this segment and exclude another segment and repeat the process until all the segments of your data were excluded, okay? And then you compare the values of the real values of concentration of these excluded segment samples, compare with the predicted concentrations, and find the errors of cross-validation, okay? These are some kinds of validation using the same samples that you are using in the training samples. Okay, this method is very suitable for a choice the number of components or variables or latent variables or PLS components that we need to use for future analysis in prediction step. But maybe there are not enough to know the real ability of prediction of the models, okay? And maybe the results obtained by cross-validation, Marena can help me with that. Tomorrow we can discuss too, or Marena, I ask you, what happens with overfitting? If you have overfitting, you fit very well your results, but the prediction ability is poor, okay? So cross-validation is a very easier way to validate your models, but it can produce or is subjected to overfitting more than an external validation. Please take care with that, okay? An external validation, what is the process for external validation? I didn't put here, but for external validation, you just need another set of samples like this. You have the equation, and then you use the equation in order to predict the concentration of the samples. And you have now the values, the predicted values, and these predicted values will compare with the real values, and you obtain the statistical error of prediction, okay? So then you can compare the errors of cross-validation and external validation if you apply both, because you can apply here, for example, in the validation step, using this calibration data set, you can use leave one out, for example, criteria for a cross-validation. You will have a cross-validation error if you can compare this cross-validation error with the error obtained by external validation set. If the errors are similar, the model is good, it's perfect. Maybe the error is higher, but the comparison means that the choice of the samples was suitable for the splitting, was suitable, but more even if you have the values in the similar scale, the same errors, say that you don't have overfitting. This is very important. But if you have, for example, here, a very small error, and here in validation, external validation data set, an error higher, you can conclude that your model is overfit, okay? So you need to improve your model in order to have a real estimation of the prediction ability, comparing these values, and please try to get similar values in this steps.
Rosario, yes, maybe I can just add, we follow a similar strategy. So we would use cross-validation in the calibration set to determine the number of factors. And if you plot your standard error of cross-validation against the number of factors, it's usually quite easy to see where you start getting an increase of your error. So we tend, we tend to use that plot to just get an idea of the number of factors to use. And as always, one rather tend to use one less than the lowest to make sure that you have a more robust. And what is really important, what you just mentioned, the similar, to make sure that you get a small error between the validation set and your standard error of cross-validation. We actually just analyzed a set of data for somebody on an instrument, and we found that there was a huge difference between the standard error of cross-validation and the standard error of prediction. Really, really huge difference. So it really seems to indicate some level of overfitting. So even if we selected the lowest RMSECV, but also what we then saw, and maybe you can comment on that, is when we plotted the SECV against the number of factors, you first see an immediate increase from first to second factor, and then it starts reducing. And it's then if you use the sort of the second lowest SECV, that really seems to be overfitted. And that's when we saw that big difference between a calibration, a SECV and the SEP. So that really seems to be a valid values to look at and make sure the difference between those two errors are really small.
Yes, Marina. The behavior of the variation of the errors in cross-validation regarding the number of EC or latent variables, maybe it's more informative than you think, no? Or that's really because you can choose the number of the latent variables looking this plot, but also you can see even if you have, I think, outliers, for example, because the behavior should be down the values of errors and then increase. So you select the value. But if you have the increase again, and then also decrease, it's all right.
Yeah.
Something happens. Something happens.
And that we saw clearly in the big difference between the SECV and the validation set. And the SEP, yes.
I think sorry, I can't, but this is the number of Latin variables.
Yeah.
I would call PC, or PLS is Latin variables, the name, the correct name. And here we have the error. For example, sorry, but this is that. Oh, sorry. This is. I will put this. SEP, for example. Okay.
O
root mean también. Root mean standard error prediction. Okay. In this way. And if you see, for example, this. This behavior, it's okay.
Yes.
Because here you have the less error, okay?
Yeah.
But sometimes you can see this behavior. It's not normal. It's not normal because you with 2 or 3 Latin variables has the suitable error, but then this error increases again. Maybe this is an outlier. Please check the outliers, and I think that you will have a normal behavior. Okay?
Yes. What you also sometimes see if you go up from 1 to 2 and then down. So if you start 1 and up.
1 and up.
Yeah, so start with 1 and then go up. So and then down. And then decrease. 1 up and then down. Yeah, so if you get that, that's also a problem. Yeah.
Problems, and you need to perform again the model and check the samples, the pretreatment, and don't use this model. The expected shape, oh sorry, it's not that, is this.
Yes.
Okay. If you have here more than one option in the valid, it's best. But you have just this one, it's dangerous. Because maybe the step is okay in the cross-validation, but in the external validation, one Latin variable will make a big difference. So please take care with this kind of model.
Yeah.
Okay. I hope to have this kind of models. Okay. Select this.
Yes.
This number of the Latin variables. Okay.
Okay.
Okay. Thank you, Marena.
Thank you.
So now we will talk about the methods to perform the calibration step, the model. And I will show you just 2 kinds of methods in order to take samples for classic and inverse calibration. And maybe this is an analytical point of view to see why we are using an inverse calibration, okay? Because the classic calibration used too many decades ago tell us that signal is a dependent variable of the concentration. If you remember the law, Lambert-Beer law, say that absorbance depends on concentration. Really, this is the concept that we used in classic calibration. But most of the chemometrics methods used for NIR spectroscopy and also other analytical techniques, optical spectroscopy, used the inverse calibration, where the signal and the concentration has the error, the higher error in concentration and not in the signal. So we will use then the inverse calibration, putting this concentration in place of the signal as the x-axis, okay? What's the difference? The difference is that now with the development of the equipment and instruments, the signal has less error of the concentration or preparation of samples step, okay? So it's better to think in this kind of models than in this kind of models. But in terms of chemometrics, there are a mathematical description similar for both, but we will change the Y and the X metrics for each case, okay? And the classic calibration will be related basically to the Lambert-Beer law, and the inverse calibration will be related especially with the method like PLS used as reduced dimensionality of data method, okay? So I will describe, sorry, I want to delete that, but okay, I will continue. Classical least square is CLS method. It's a very well-known method used for application of Lambert-Beer law, okay? This method allows simultaneous determination of concentration of all components in a mixture of samples where you are using a higher number of variables. It's perfect for a spectroscopy, okay? And it has an advantage. It provides as output the pure spectrum of each component, even if you don't have the pure spectrum as input, okay? You will have the pure spectrum of each component as output after the application of the method. It's mathematically easy to understand, and the process is very, very similar to the classic application of a Lambert-Beer law, okay? If you remember the Lambert-Beer law, said as that the absorbance depends on the concentration and also of the epsilon coefficient, extinction coefficient, if you remember, okay? So in algebra mathematical, you can see the equation like that, okay? Absorbance or signals depends of the concentration. This is concentration, X is concentration here, and one slope or one matrix, call it in this case, K, okay? This is the simple regression. Okay, in the first step, in the calibration step, you will use this equation, absorbance is equal to X multiplied by something, and you will find this matrix K, okay? This is the first step. You have one X matrix with different samples with mixture of components. How many components? This is a problem because if you want to use classical least squares, you need to know how many components you have in your samples and even the concentration of each sample of each component in each sample, okay? Because you need here signal absorbance and concentrations in X. But if you are working with real samples coming from foods, for example, or coming from natural resources or vegetables or soil, for example, you don't know the exactly number of components unless you know the concentration of each component present in your sample. This is impossible. Maybe this method is very suitable for application in pharmaceutical industry because you, in the case of drugs, in the case of pharmaceutical products, you can know all the components. You can also the concentration of each component in each sample. Okay, this is a special method, but it's easy mathematically because if you have this kind of samples, you can find this K value, and then in the validation, you will use another data set, validation data set, and you will have your absorbance of your data of validation data set, and you will use the same equation. You will use the K obtained in the first step, in the calibration step, and you will use the pseudo inverse. This K has to the other side a pseudo inverse of the matrix, and you will find here the concentration, the predicted concentration, X hat now. And this is the value that you will compare with the X values, the real X values or concentration values of your validation data set. And that's all. You then need to perform the error analysis, and the error analysis give you acceptable errors, so you are ready to use this model for prediction. In a prediction step, you just need the absorbance of a new sample. You have the K matrix obtained in the first step, and you will have these new concentrations for samples, for unknown samples, okay? And that's all in case of classical least squares. But this matrix K has a lot of information, qualitative information. What kind of information has this matrix? This matrix is the called sensitivity matrix containing the pure spectra of the compounds. For example, we have here a determination using NIR spectra of two systems of samples. Here we have, for example, benzene, cyclohexane, and ethylbenzene. We don't need the pure spectra. That's not necessary. It's only shown in order to see that we have some difference in the spectra, but we have also overlapped those signals. So univariate analysis, it's impossible, and you need to apply multivariate analysis, okay? But if you have, the system has three compounds, you can apply CLS as method. What is the advantage? You can measure different samples, like this one, for example, sample number. Here we have around 20 samples, and you can obtain the spectra of the 20 different mixtures of samples, mixtures. You don't need the pure spectra or reference or standards spectra. You just need the spectra of the mixtures, and then you apply the method using this step of the calibration. You will obtain this matrix K. If you plot the matrix K, the matrix K will give you this kind of result. I mean, the pure spectra obtained mathematically of each component as output of your sample. It has a lot of qualitative information because you can identify the bands, you can identify the profiles of the compounds present in your sample, okay? Even if you don't have a standard or a chemical pure reagent to use in the calibration, you don't need it, okay? So you will find this component, but you need to know how many rows and columns will have this K matrix, assuming the number of components, okay? You need to know that. And this is an advantage of CLS. This method works very well in case of a spectrum. This is a multi-channel advantage, and it works also very well in case of compounds with a high number of components, even if you are using, for example, 10 components, 9 components, but you need to know which component is and the values of the concentration of each component. This is a problem, okay? Mathematically, it's very easy. But if you don't know the chemical composition of your sample, or it's impossible to know this, how many, estimate how many components your sample have, so you can use this kind of methods. Partial least squares is an inverse method. This method assumes that the error is not in the signal axis, but in the concentration axis. Okay, these are more realistic methods for calibration using this kind of instrumentation, like the NIR spectroscopy. PLS is the most used multivariate method for quantitative purposes in analytical chemistry. If PLS doesn't work, you can test new methods, you can prove, you can combine, you can pre-process your data, but normally PLS gives good results in most of cases compared with most of the regression methods using as multivariate approach. Maybe you can fit some strategies in order to remove some variables, in order to select very important variables, variable selection. This is known as variable selection, but PLS is the most powerful tool until our days, okay? But how works PLS? It's not so easy, but I summarize the steps like the CLS processes, but you need to know that each matrix X and Y, now X is not concentration, now X is signal, and Y is concentration. And each matrix X and Y will be decomposed in two matrices, scores and loadings, you know that, like the PCA step, okay? It's the similar PCA, but the difference mathematically is similar, but the difference is that now you will have scores and loadings, but you will need to project these scores obtained in the PCA step, that these scores will projector and covariate simultaneously with this response Y, okay? You will find mathematically maximize the relationship between the scores produced in this composition of X matrix regarding the property that you want to measure, okay? You, for example, want to measure density of one product, okay? Wood, for example. So you have the values of density and they are plotted as this violet line here. And you can see here the scores of different components. Here have moving different components and projections to the scores to different components, and you will find the latent variable principal component which vary at this point, because this point is very related to the answer that you want to estimate, okay? So maybe this principal component is not the first principal component obtained by a simple PCA. I mean, maybe the first or second PCA is not the vector more related to the parameter that you have to estimate, okay? You need to discard this component and you need to work with the component most related to the answer. So selection of components is different to PCA, because in PCA, you just need to find the components, the first component, as the vector describing the maximal variance of your data. But in PLS, the first PLS component is the component which describe the maximal variable of your data, but which covers simultaneously with the response that you want to estimate. Okay, this is the difference. Sometimes it's the same, sometimes not. Okay, you will use the term PLS component and no PC, just principal component, in order to clarify this difference, because they are not the same. And normally we use the name latent variable for this new principal component with a maximization of the relationship with the concentrations in this case, okay? And the mathematical step is not so easy. I will describe just a general expression. Here we have the same thing, but Y now is the concentration and X is the signal or NIR spectra of the calibration data set. And we will try to get some mathematical explanation of this regression using this kind of regression. Y is equal to X multiplied by a vector that we need to find, plus an error, and this error is known as residuals, okay? And we'll have irrelevant information containing the values of the contribution for other latent variables or PLS components that are not important for the calibration, okay? But you need to find this value B, okay? This value B is no regression vector. And in the calibration or modeling step, you just need to obtain this value using the pseudo-inverse of the X matrix, which pass to this part of the equation, and you isolate this value B, and you find this regression vector. And the second step, you need the spectra of your validation data set. You will use this value of B, of the regression vector. You will multiply this value and obtain then the predictor value of the concentration of this validation data set, okay? And you can compare now the concentration, the real concentration versus the predicted concentration, and estimate all the statistical parameters to analyze the error performance and decide if the model is okay, if the error is enough for screening, enough for analytical determination of the analytes, and so on, okay? And then if your model is okay for prediction, you can apply the model for prediction of new samples where you need just the spectra of the sample because you have the vector, the regression vector, and you will find the predicted value of concentration, okay? It's the same like a CLS, but you change now X and Y because X now is the spectra of the data. Now we have an example what we can do with PLS, for example. PLS is a special method for quantification in presence of interference in your data calibration samples, but you can quantify different chemical, physicochemical properties, okay? For example, we have here the application of PLS for determination of the polyphenolic content and antioxidant capacity and alginate content of the algae thrown by PLS in mid-infrared spectroscopy and in near-infrared spectroscopy using NIR data, okay? We will check the second part because it corresponds to the near-infrared spectrum, okay? What is the output of this method? The output is the concentration, the predicted concentration. If this predicted concentration is used and compared with the measured or real concentration measured by the reference method, and then we will estimate some errors, okay? And these errors are very, here, diverse. We have different errors. We have an error corresponding just to the calibration step, and we have another error for the cross-validation step, and we have another error corresponding for prediction of external validation data sets. And before to describe this, I want to ask you if you have some questions before to describe the estimation of the errors. Yes, it's okay? No questions? Okay.
Hello, can you see me? My name is Hani Alam, and I'm from it. I would like to ask, so the classical least squares is for samples we know all of its components, right? While the partial least squares is for samples we don't know exactly all the materials and the concentrations. So let's say we
if we know, let's say we know the materials that we know some of the materials of it, and we know we want to know the exact concentration of one of these materials inside it. Can we like use PLS? Should we use something else, or?
From the point of view of the mathematics, yes, you can use PLS, but CLS, no.
No, should we use
PLS? Yeah, but if you have an approach of the concentration of the component that you want to estimate, even if you don't have how many components you have, how many interference you have, no problem. That's no problem. That's doesn't care. You just need to have a value, a column with the values obtained by the reference method. I mean, if you want to quantify one component of your material, you need to use estimation, a value of this component obtained by a reference method. The reference method is mandatory. If this reference method has a higher error, standard deviation, for example, it will be affect your model too, okay? Because you are building your prediction tool using this high error of the reference method too. So if you have a reference method with the less possible error, it will be better, okay? Okay. It will be better. If you have an estimation, okay, you can find if NIR spectroscopy is useful to estimate for screening, but if you want to quantify with statistical or good errors and an analytical way with uncertainty acceptable, you need to use a correct reference method. Okay.
Okay, thank you very much.
Okay, so we can see here. I go back. Thanks, Hannah. So you can see that the main plot that you need to show after the application of a regression method is a fitting between the predicted and the measured values of concentration. And we hope that the samples are very close to this line at 45 degrees, okay? That's a perfect model. But I think that in use of NIR spectroscopy, near-infrared spectroscopy is not, you don't need to expect that the samples are all the time on the line. No, it's normal, this kind of distribution. Marena show us a table with the values of coefficient of determination, and this coefficient of determination is related to the variance explained or the information explained with our model, okay, under a determinate number of latent variables. But also it's important to see that dispersion of sample, variance of samples should be around this line, but it's not normal to see the points on the line because maybe this is a realistic model with overfitting. Maybe you see very good model, but in the prediction, it's difficult, okay? Please take care because in near infrared spectroscopy, the values of error or coefficient of determination or regression is not 0.9999 as in a univariate analysis in some applications of components without presence of interference. Now, in this case, interferences are there. And this is the goal. This is the goal, is to develop a rapid and good model, avoiding the use of chemicals, avoiding the waste generation, just with mathematical and optical spectroscopy. But the risk is that the values of the coefficient don't need to have this kind of value, 0.999. If you obtain this value, wow, perfect. In the prediction and the validation, external validation, if you obtain a very, very small error and a very high coefficient of determination, wow, it's good, very good. But it's normal to see this kind of plots in infrared, in PLS analysis, okay? So you can see this as main strategy to visualize the success of your analysis, but you need something more quantitative, okay? And this quantitative is estimation of the different parameters. Marena show us these values too, maybe with SEC, SECB, the cross-validation, the standard error of cross-validation, and standard error of prediction. I will use the notation root mean, standard error of calibration, because we are using the quadratic root mean. And here you have the difference between the real concentration and the predicted concentration, just for the stage of the calibration. I mean, this first step, just this fitting. This fitting is nothing for prediction. It's nothing no. It's just to see if we have some relationship between signal and concentration, no more than that, okay? And then you can estimate the root mean standard error of cross-validation using the difference, but now using some authors put here n minus k. K means latent variables, in -1, 2. It's also possible to find this description, okay? I will include this in another slide. And cross-validation is the same, but now we are using the same samples excluded from the calibration data set, removing the sample and predicted the sample with the rest of the training samples as model, okay? This is the standard error of cross-validation. And if you predict with that external data set, you just need to calculate the difference between the predicted and the measured value of concentration, divided this value, sum of the square of these values, divided by the number of samples and has the square, okay? And you will have here another error of the external validation. What we can expect that this value of cross-validation, error in cross-validation and error in the external validation will be similar. If we have more error here, a little higher than cross-validation, it's even normal because this is more realistic, okay? But just a little, not too much, please. Because it's too much, okay, they are overfitting. We need to improve these values in order to have values more similar, okay? And then we can estimate also the value of the coefficient of determination. It's very important because we will see some, this is a parameter of relationship between the Y and Y and predicted Y, but it will describe also the variance of the model, okay? The variance describable the model using a determinate number of latent variables. So if you have error almost of 100%, it's perfect. More than 19, I hope so. It's not easy, but we expect these values, okay? And then we can calculate different analytical figures of merit that I will define tomorrow with more details, okay? I will back to this slide in order to describe another parameter that you need to calculate or visualize, please. Here we have the regression coefficient. This is the plot of this value, B. This is the vector, this is a vector B that in NIR spectral data, you can use in order to have an explanation of which original variable is contributing to your model and choose to select which variable is most important, okay? For example, here you have the regression vector for polyphenolic content, here for antioxidant capacity, and for the content of the genetics. So you can decide which variable contribute more, for example, for the polyphenolic content. Here we detect the values with a major contribution. Here, for example, this variable are very important. And this region is not so important. And even we have here noise explanation means that this region is most important than this region, okay? Probably I need to delete this region, but probably the model doesn't improve. So maybe the complete range is needed, okay? So you have here qualitative information from a quantitative method. But a disadvantage of PLS methods, a difference of the CLS, is that you don't know the pure spectrum of your compounds, okay? For example, if you have something, polyphenolic content is a property. But if you have, for example, a compound, for example, benzene, if you want to quantify benzene, you will not find benzene here, the profile of benzene, but you will find which bands are correlated to the benzene spectra, okay, contributing in more to the model, but you will not find the pure spectra of the compounds. This is a disadvantage, but the goal is to quantify for PLS. It's not identify, okay? There are methods that don't need to know how many components you have, don't need to know the concentration of each compound present in your sample, and gives you the pure spectra as output, and gives you a concentration value, a predicted concentration value. I mean, there exists a method with characteristics of CLS, of PLS, and more. And this method is called multivariate curve resolution. You will see this method tomorrow, okay? But exists. But normally, PLS is a more powerful tool in order to quantify. And MCRLS, a new method that we will be tomorrow, but we'll see tomorrow, is a method with another objective, is to obtain the pure spectrum, like CLS, okay? But when you are working with complex matrices, like foods, for example, okay? But for PLS, this is all that qualitative information that you can obtain from this method. Interpretation of these bands, I asked to Marena, how can do an interpretation of this band? It's not easy. You can detect with PLS, as chemometrician, we say that we can detect the method. Okay, but you want to know what happens, an overtone, combination bands. Okay, we try sometimes using these kinds of handbooks or papers like this. Marena, you know, maybe this atlas for spectral interpretation, but sometimes we say, oh, it's so I don't know.
I must agree, it is not easy. It's not easy. Sometimes, yeah, we use the tables for William's book, Brian Osborne's books. There's many tables that you can look at. Some of the companies make these huge sheets that you can put up on your lab wall to try and follow. But it is not necessarily easy. Moisture peaks, if you work with moisture protein, that's typically easy to determine. But when you start working with more complex samples, such as the algae that you're working with here, and you don't necessarily know what to identify, it is not easy. It's not easy. So sometimes you're lucky that some other people have done some work on similar commodities. You can consult their work, but it really is not easy to interpret these plots. Yes, it's not easy.
It's a difficult task. Okay.
Rosario, I just want to ask you something else quickly. Just going back to what you said, that you really look at the SECB and it's actually the drawing that you still have on your slide, that your SECB and your SEP should really be as close as possible to each other. We actually noticed at some work that the SECB was much higher than the SEP. And that's not normally so, and would that also indicate overfitting?
Not necessarily indicates overfitting. That's true. That's true. Not necessarily indicates, but it may happen because the depends on the difference. If you have a big difference, that's because you are using, and it's possible to have this kind of results if you have one sample, which is removing and saying all the results. Because this sample, for example, is an outlier or it's an atypical sample, it's a little different, and saying all the results. Because in cross-validation, you are removing one.
Okay.
Okay, it happens. But it's not necessarily say that it's overfitting if you have some difference. That's real. That's real. But if you have a big difference, something happens because the behavior is different of the two data sets.
Okay.
Yes.
So it might mean that there's a huge outlier that's really affecting the SECB results. So one just need to go and check for outliers. Okay. Yeah, that makes sense. That makes sense. So there was definitely, it was because typically you might get a small SECB and a slightly larger SEP, but it's not often that you see the large SECB and the smaller SECB.
And even sometimes if you use an external validation data set, maybe you can obtain a less value for RMSEP compared with the cross-validation error.
Yes, yes.
Oh, wow, it happens too.
Yes, what happens? We have a lower SEP than the cross-validation, and I think what the problem might be is maybe a huge outlier in the SE, in the calibration set.
Yes, yes, and maybe you need to change the strategy to select the sample to split the data between calibration and validation. I mean, the problem probably is in this stage.
Yes, that something was not well selected.
We need to back in order to obtain a more homogeneous samples in both data sets. This is the problem.
So this is really something unusual that we've seen recently.
Yes.
Yeah.
Yes.
Okay.
So,
okay. Yes.
And for cases where it's very, very, very difficult to obtain more spectra to construct a external validation data set. So maybe leave one out cross-validation is a solution, but maybe we can test another cross-validation method too. Like to remove more samples or use this K-fold or Venetian blends is the same.
Oh, yes.
Are more realistic methods to evaluate the prediction without to increase the number of samples obtained from different places. For example, here, Marena, my student, works with a plant, very difficult to get because it's so far, it's protected species, it's not easy, the time, the season, we don't have more. And pandemic reasons too.
And based on what you've just said, I want to maybe just point out to the students that when you do NIR work, and especially when you start doing the data analysis, doing one round of analysis is seldom enough. So you would often do something and reanalyze and try something again and reanalyze. So it really, so you shouldn't get disheartened if you get asked to repeat again, try again. This is often the case.
And they are experts.
Then you are experts. Once you've tried everything, you're right. Yes.
Okay. And to finish, I think, let me see some explanation of the tables, because tomorrow we will see with more time these analytical theories of merit. And now I want to show an example of the table with the parameters that Marena taught us in the morning, a lot of parameters, statistical, but the minimal information that you need to inform to the readers, to your teacher, to your company, it's at least with a kind of pre-processing and transformation are you using, okay? What is the number of PLS components of latent variables that you are using? For example, in this case, and this is mean centering, I use the first derivative. If I use the first derivative, how many points of the window I need to explain in detail in order to have then reproducibility and validation correctly, okay? The model will apply the same transformation and preprocessing techniques that you are using for calibration step. If you have an external validation data set, the model will apply the same preprocessing transformation and then will estimate the values of the concentration using the equation. But if you apply the equation directly without this step, it doesn't work, okay? You need to report the PLS component. You need to report the number of samples that you used for the build of the model, the explained variance, the range. This is very important because if you put just the errors of cross-validation, calibration, and external prediction, and you compare the data, you can decide if the model it's okay, if the values are similar, but you don't know how, because this has the units of the measurements of concentration, but you don't know if this model, if this error is low, is higher for your purpose, okay? So the range is very important. And then you can also infer another parameters. For example, in this case, I show you the ratio performance deviation as comparison between the error or the reference method used for quantification, compared this error, in this case, with the error of prediction, okay? And this is this value. We saw in the morning how higher or lower have to, this number have, because we need to evaluate if the model is ready for prediction or no. 3.8 in this case for us, for example, in an analytical tool to determine the quantification of polyphenolic or antioxidant capacity of the algae, it's okay because this is a biomass, it's very variable in the sea. But if in analysis of a pharmaceutical product, for example, could be not enough. I mean, it depends of your purpose. It depends of your samples and of your goal if to determine if this error is enough or not in reporting in order to know if someone can interested in this kind of error or not, that it doesn't work, okay? So we estimate here cross-validation and prediction RPD. We use both, but obviously in the external validation RPD calculation, it's better maybe because it's more real, okay, for prediction. And another parameters, Marena showed in the morning, a lot of parameters. Part of this, there are the, for example, error of the reference method, the coefficient of regression, coefficient of determination. You can put all this information, but it's needed to estimate how is this error compared with the range 2. And you can also use this value, divide this value by the mean of this range, and you will have a relative error or prediction in percentage. It's not here in this table, but you can estimate it. The relative error or prediction in percentage. Because in percentage, you can imagine the error. 2%, 10%, it's higher, really. 5% maybe is normal, but 25% is too high. So you can estimate the error using this rep tool, okay? Among other parameters, very important to report, but please don't forget this stage. And even you can analyze this table using the same property, the same data, the same spectra, the same sample, the same range, and just comparing different preprocessing and transformation techniques, and you will see difference. And this is part of the chemometric work. This is the real optimization step of the chemometric model for quantification. The preprocessing and the transformation you use in your model building, okay? So tomorrow we will work. Today I add this slide while Marena told us about the slope. Marena, you told us about the slope. Tomorrow I will translate this slide because I didn't include this slide, but today after your presentation, I was thinking in the possibility to show you tomorrow one method to evaluate if the slope and the intercept are statistically equal to 1, and 0. Okay, so tomorrow we will see this.
I think yes, it would be great if you can elaborate on the bias slope issue. I really appreciate it.
And then we will describe some analytical figures of merit. So, questions?
No questions? Yeah, I think you've covered quite a few questions while you were presenting today. So there might be, once they slept over it, there might be questions tomorrow. So yeah, so if you're done, Rosario, thank you very much. I'll just, yeah, thank you very much.
Continue, eh?
Is that?
Sorry, I check in for something, maybe so in a rapid way. I can describe something very, very fast. Just give me 1 minute, please. Because I want to show just the importance of the regression vector. Okay. This regression vector is used normally in methods of inverse calibration to estimate a very important parameter, color sensitivity, okay? Sensitivity is the word here. An inverse method like PLS, PCRs, and ALS, you can find the sensitivity of the model divided 1 by the Euclidean norm of the regression vector. So it's very important because normally we don't report the sensitivity of the models, but we can do it using this regression vector. This is another contribution of the PLS model. But the inverse method has a problem in comparison with the classical method like CLS, is that if you want, for example, to estimate another parameter like selectivity, you need to use the pure spectrum of your components. But in CLS, you have this pure component because is the pure spectrum because you have as output this spectrum. But in PLS, you just have a regression vector and you don't have the signal of the pure spectrum. So the disadvantage to use in analytical terms to use the inverse calibration, like PLS and PCR, principal component regression, that is similar, is that selectivity could not be estimated. Okay. It's just estimated from CLS or classical least square calibration or Nir calibration or classical calibration, because you have a pure spectrum. So selectivity is impossible to be estimated from PLS, but it doesn't care. People work with PLS because they don't need to quantify selectivity, but the selectivity is highly improved with the use of any chemometric methods, even PLS. If you don't can to quantify this difference, you don't estimate the selectivity value like other methods, but you improve the selectivity, yes, you can improve the selectivity. And the goal of all these methods is precisely to improve the selectivity to have a good prediction of concentration. Okay, so this is part of the explanation about the advantage or disadvantage to use classical versus inverse calibration. Okay, Mike, tomorrow we will continue.
Okay, so we're calling it today, Rosario. Thank you. Okay. Yes, thank you very much indeed. Thank you for your time this afternoon. Thank you for everybody attending today. So tomorrow we will start again at 9. So I will continue again at 9. I'll go through my slides and see if I have to. I think Rosario probably covered everything that I didn't do this morning based on the calibration and in a very clear and understanding manner. So I will then continue. We will look at instrumentation. So I'm going to spend a little bit of time just discussing instrumentation as such. I'm going to discuss reference methods, and then I will look at factors overall, not in terms of chemometrics, but overall factors that can affect the accuracy of your model. That's in terms of sampling the instruments. So just a session on the factors that can affect it. And if there's time left, I might just refer to some applications. So that will be tomorrow. And then Professor Rosario will continue with chemometrics, classification, amongst other things. And also you want to do curve resolution as well. So she will continue with the chemometrics session tomorrow afternoon. So thank you all for being here. I think we sort of, some people disappeared during the course of the day. Hello, Mejit, good to see you here. So
I just want to also say hi to Rosario and thank you also for the lectures.
Okay.
It's now reasonable time, or you will sleep now, probably.
Oh, yeah.
Now her day starts. Her day starts exactly now. So she still has a long day ahead of her.
Okay.
Yeah.
Okay.
Thank you all. Yeah, so we're looking forward to see everybody tomorrow morning at 9.
Okay.
Thank you. And
I see Martin is there, so he will be in Turkey very soon. Hi, Martin.
Oh, yes.
He
didn't sleep. He cannot sleep.
Oh, and Hilmi is actually in the lab now. Hilmi, are you in the lab?
Yes, yeah, I am in the lab.
And Hilmi as well.
You're all in the lab. Okay.
So I was in my home for the first part, and then
now you're in the lab. And Hilmi also. Hilmi, were you at home for the first session?
I think. Not now.
Not now.
Sorry, now I cannot.
It's in the lab.
Oh, Macarena is there too.
Oh,
we are in the office.
Okay.
Nice to see you all there.
Yeah.
Okay. Right.
Okay.
Thank you.
Take care then. Thank you so much.
Thank you very much. See you tomorrow.
Bye. Thank you, Rosario. Thank you all. We'll see you tomorrow at 9.
Bye-bye.
Okay, bye. Keep well.
They go to here.